Et venez de ce côté. Non, venez pas.
Ouais.
Okay, good morning, good afternoon, good evening, we don't know. We're pleased to welcome you for the workshop on population dynamics. So we're going to start with some introduction. I'm Olivier Jimenez. I'm working in Montpellier in statistics and ecology at the interface. And the other lecturers and helpers will introduce themselves. Sarah, you want to try?
Hello, I'm Sarah Kubain. I'm working at the CEF and I'm working mainly in evolutionary demography.
Hi, I'm Aurélien Bénard. I'm working at the CEF too, and I'm a specialist of population dynamics for conservation biology.
Hi, I'm Thierry Chambert. I'm also working at the CEF as a postdoc, and I'm a quantitative ecologist.
Hey, I'm Valentin Lauré. I'm doing a postdoc here, and I'm working on statistical ecology and data integration.
Hi, I'm Thibaut Couturier, working as an engineer here with a protected area in France on wildlife monitoring populations.
Hi, I'm Javier Fernandez. I'm working as a postdoc here in species distribution models and these things.
Hi, I'm Marwan Nassiri. I'm a PhD student at the CEF, and I'm working on population dynamics and demography.
Yeah, and we're missing, I think, Lisa, but she'll introduce herself later on. Okay. Oh, Lisa, are you here?
I'm here, but I'm in another place. So hello everyone, I'm Liz, and I'm a PhD student at CEF, and I'm working on demography and movement of birds of prey.
Okay. Thank you. Okay. Can you hear us well? Is that okay? Yes. Okay. Thank you very much. Okay. So we're going to start by a short introduction. Okay. So we're based in Montpellier. Sadly, we couldn't host you all in Montpellier, but we're happy to have you all on Zoom. It's a way to accommodate a lot of people, so it's kind of nice in that way. Okay, this workshop started last year, and we had this crazy idea to have a free and video recorded workshop open to everybody. And it started on Twitter, and then we got a lot of attendees last year, and we decided to do it again this year. So welcome again. So we're going to talk about quantitative methods for population dynamics. So population dynamics is this discipline where we study the evolution across time of abundance. And so we're going to have a look to the outputs, the abundance, population size, and also we're going to have a look to the processes that drive population abundance across time, namely birth, immigration, death, and emigration. So we're going to have a look and go through methods to estimate population size and density, and also demographic parameters. So that's the aim of the workshop for the 2 days we will spend together. And also, in the third lecture, we will learn how to project population size in the future using population projection models. Okay, this workshop doesn't come from nothing, so credits and inspiration. everything started in the team with past workshops on capture-recapture models that we used to run with Roger Pradel, Rémi Choquet, and Jean-Dominique Le Breton. And also, we did organize this workshop a long time ago in 2007, back in Greece, on population dynamics, and yeah, so it's almost 20 years. And we had a long pause and decided last year to resume, to revive this workshop because maybe we thought it would be useful to some people. And also, there are some slides and material that we use from lectures that we do with Olivier Durier, a colleague of ours. Okay, the lecturers, we've already introduced ourselves, the helpers as well. So on our plate, what's the program? First chunk of lectures and live demos is going to be about estimating abundance and density of populations. Then we will go through a lecture and live demos about how to estimate demographic parameters, survival, dispersal, and so on. And the last one, so tomorrow, population projection matrix models that will give you all the ingredients to be able to project populations in the future. The way we've designed the workshop, the philosophy of teaching, if you want to use big words. So it's a lot of attendees. You are, I mean, it was more than 1,000 people who registered for the workshop. It's cool because it's on Zoom, so we can do that. But it means that it's also you're coming with a variety of background, heterogeneity in knowledge of statistical analysis and methods in population dynamics, and also in R. So we are aware of that. So we've tried to accommodate that, but it's not easy, as you can imagine. So we hope that everyone will find something to take home. So it's going to be a lot of material in 2 days, but everything is available on the website, and also everything is video recorded. So you can come back to the workshop later on if you haven't understood something or if something isn't clear. You can, and also we will see how to ask questions and so on in a minute. Okay, so don't put too much pressure on yourself. You won't, if you start from scratch, you won't understand everything during the workshop in 2 days. You will need time to digest everything, but it's a normal process. All material, including videos, are on the website, like I said, and feel free to play around with the material while we walk through it, and afterwards, of course. So the workshop is organized in modules: population size, demographic parameters, and matrix models. And each model is a combination of lectures. So we will talk, and then we will demonstrate analysis using some R packages. Okay, so that's the combination we've gone with. So how will we interact with each other? So it's a challenge too, because it's a lot of people again. So the way we've decided to go with is to use 2 things in Zoom. Sorry, it's not on YouTube, it's on Zoom. So maybe I can try to show you that. I'm going to share my screen. Yeah. So there are 2 ways to discuss and interact. You can have a chat, say hello, I don't know, interact with each other using the chat in Zoom. If you want to ask questions, we will use the question and answer option in Zoom. Okay, it will help us to organize the questions, also to pick among the helpers and the lecturers who will answer what question. Okay, so please, if you have questions, and you will have questions, use the question and answer option in Zoom, right? Okay. And I think that's all. Huh? Yeah, that's all. Okay. So we're done for the introduction. So now we're going to start with the first bunch of lectures by Aurélien Bénard. on estimating population size and density. Perfect.
So can you see my screen?
Yeah, that's perfect.
Okay, great. Nice. Okay, so thanks, Olivier, for this introduction. So in these first courses, I will talk about how estimating abundances or population size. Okay. So as Olivier told you just before, the population dynamic is the study of a variation of population size over time. And in these first courses, we'll talk only on how to estimate abundance, population size, or density. So let's begin with a very simple example. We would like to have an estimate of abundance of a species, this small tortoise here on the screen, in the field. So to do that, we go in the field and then we count the individual that we detect in this area, this study area. But of course, here we count 5 individuals. But as you may all know, we can miss some individuals during the count in the field. So here we missed 3 different individuals that were present in the study area just because they were hiding in the vegetation. So this is a very common source of bias when we count individuals. The detection is rarely, maybe even never, exhaustive. We systematically miss some individuals. So this is true for animals, such as tortoise, birds, or mammals, but this is also true for insects, amphibians, and reptiles. But this is also true for fishes, for example, in aquatic environment, or even plants. So there is a lot of good reason to miss some individuals in the field. For instance, because the observer that goes to count the individuals, they lack the experience on how to detect all the individuals in the field. It can be also because the weather is too cold for the individual to be active, for instance, and then you miss the individual because they are hiding in the vegetation or in the ground. And it's in plants, for instance, it can also be because of phenological issue, because it's much easier, for instance, to detect plants when they are flower than plants that are very small at the beginning when they emerge. So there is a lot of good reason to miss some individuals when we are working, counting individuals in the field. But the conclusion is that when you miss some individual, the raw count are a biased, an underestimation of the true population size you are interested on. So let's move a bit. Very often in ecology, we would like to compare the abundance or the densities at different sites. For instance, to get some information on habitat selection of a studied species, or to assess whether the management actions that we dedicated to these sites are efficient or not. So here we have 2 different sites, site A and B, and we go in the field and then we count again this small tortoise. So you can see here that on the site A, we detected and counted 4 tortoises, and then on the site B, we detected only 2 tortoises. So the crude conclusion is that the site A is better, is suitable, more suitable for the species than the site B. But also, you can see in this the slide that the vegetation cover, the density of the vegetation is very different between the 2 sites. And probably we miss more individuals in the site B because the vegetation was the denser in this site B. So the conclusion with that is that the detectability is usually varies usually over space, in space, and that when we compare the raw data from the count, we can make round inferences regarding the spatial variation of the densities we are studying. If we go a bit further, most of the time in conservation biology or in ecology, we are interested in temporal variation of abundances. For instance, because we want to classify the species as threatened or not, or because we want to have an estimation of the trends of the population, or because we want to check whether the management actions we dedicated to the site is efficient or not. So to do that, we use something called the monitoring. We go on the site at several time interval, and then we count the individuals we detect. So here we go on the site first year, and we detected 5 tortoises. Then we go 10 years later on this site, and we count only 4 tortoises. And then we go back to this site 10 years later again, and then we counted only 2 tortoises. So here, the crude conclusion is that the abundance of this species on this site is declining, strongly declining, so that we need some management action, for instance. But again, you can see here on the slide that the vegetation structure changes over the time. Notably, it increased a lot over the time period we studied. And probably in this situation, we miss more and more individuals because the detectability decrease with increasing of the vegetation cover. So this is again a rule in ecology, in spatial ecology, or temporal ecology, when we have detectability usually change over time. Most of the time it changes over time because a lot of things can change over time. You can have, like here, the vegetation structure that will change over time, but you can also change the of an observer, or the phenology of a species can change with climate change, for example. So to make a short conclusion to these first 3 slides, when we have detectability issue in ecology, and this is the rule most of the time, it's true, then we underestimate the population size, we make wrong inferences over regarding spatial variation of abundances or densities, and we make also wrong inferences regarding temporal variation or temporal trends or temporal variation of abundances. So if we try to formulate that using a small equation, we will note for the rest of the courses the abundance at a particular species at a particular site, the n. This is the true abundance of the species on the site. And then we will not see the number of individuals that are counted in the field when we go on the field to count them. And if you have C and N, we can write that the expected value of C, the expected counts on the site, is given by the multiplication of 2 parameters, the true population size, but also a second parameter that we will call P in the rest of the workshop, that is the detection probability and sometimes the capture probability. So this means that the count are made of 2 components, the true abundance and the detection probability. And of course, if we would like to make some inference of N using the raw counts, we have to have information on P, or at least try to estimate P. Okay, so the number of counted individuals on the site divided by this recapture, this detection probability P, and I introduce here another parameter that we call alpha, that is the fraction of the study area that is sampled. I will go back to that a bit later. So if we want to have an unbiased estimate of N, we need to estimate P. Here, the fraction of a study area that is eventually sampled. There is a lot of theory and empirical works on how to select sample units in the study area to obtain unbiased estimates of abundance. And it's a relatively complex task. We need to define a kind of statistical population of sample units, usually plots. And we have to rely then on some random selection process of this unit among the population of sample units. We have a lot of different type of design to do that. We can use random sampling, systematic sampling, stratified sampling, spatially balanced sampling. But we won't develop this aspect in this course. we should develop an overcross to do that. If you are interested in this subject, you can have a look to these two books. The second book, Sampling, from Stephen Thompson, is specifically dedicated to the sampling theory in ecology. And the first book, Analysis and Management for Animal Population, written by Williams, Nichols, and Conroy, is the kind of Bible for population monitoring, for people working on population monitoring. And you will find a lot of material regarding sampling design in this book. And this aspect of sampling design is true for animals, but also for plants and for all type of animals. Okay, so the main goal we will have in the next courses during this morning and early afternoon is to estimate P, the detection probability of the individuals when we go in the field. So several methods exist to do that. And the use of the method depends on whether the population we are studying is considered as closed or open. So just to be very brief, for closed population, we have three different capture-recapture again, and the open and mixture. So in this course, we will work only in this course this morning and early afternoon. We'll speak only on capture-recapture for closed population, distance sampling, and mixture for closed population. But in the later afternoon, you will have some information on how to estimate demographic parameters for open population. What is a closed population? So the hypothesis, the assumption that the population is closed to use this method means that the population is close to is demographically closed, meaning that there is no birth and no death during the study of a population between the first field session and the last field session in this population. And also that the population is geographically closed, meaning that there is no immigration in the study area or emigration out of the study area between the first field session and the last field session we are considering in the analysis. So this implies to work over relatively short time intervals, but the term short is highly dependent on the species you are studying. For instance, if you are studying this Hermann tortoise here, that have very low dispersal capabilities and a very long, high longevity, high survival and long longevity, then you probably can organize your fieldwork over several months or at least over several weeks. But if you are working on butterflies, whose survival is about 10 days or 15 days, and that have very high dispersal capability, then you will have to organize your fieldwork over a very short time interval, few days, and sometimes even at the scale of the day. So you will have to define your sampling design, your protocol, depending on the species you are studying. We won't develop that much here. So let's begin with the capture-recapture for closed population. Let's say again that we want to have an estimate of the abundance of the tortoise in this site by doing fieldwork. So we will go in the field and sample individuals in this study area. We prospect, we survey the site haphazardly, and we detect some individuals. We capture them, we measure them, we mark them. For instance, here we detected 5 individuals that we measure and mark with a dot of paint. Just a dot of paint is enough. And then we release the individuals in the study site. Here you can see that when we conducted this field work, we missed a lot of individuals. And of course, the row count of individuals we detected is an underestimation, a strong underestimation of the true population size. Here, the detection probability is about 1/3, but of course, we don't know this value. So the number of detected individuals at this first field session will be noted N1 for the rest of the workshop. Okay. So we leave a few days, and then we'll come back to the study area, maybe 1 week later or 2 weeks later, and we again survey the study area. We prospect the entire study area haphazardly, And again, we detected some individuals in the field. We know that we missed some, but we detected some. Here, we detected 6 individuals. We have a second number that will not N2, that is the number of individuals detected at the second visit on the site. And among these detected individuals at the second session, we have some individuals that have already been captured at the first session and then are already marked. And we will note this number, M. M is the number of individuals that have been captured at the first session, mark and release, and then capture at the second session. Okay, so we have 3 quantities, N1, N2, and M, and we can try to organize that using some equation to get an estimate of population size. So we have the proportion of marked individual after the first sample that is given by N1 divided by N, the true population size. We have the proportion of marked individuals in the second sample that is given by M divided by N2. And if we assume that the sessions are independent, so that the individuals have equal detection probability, whether they have been already captured at the first session or not, this is very important. I will go back to that a bit later. Then the proportion of marked individuals in the second sample is very easy to obtain. It's using a simple rule of 3. It is the proportion of marked individuals in the entire population. So the proportion of marked individuals in the second sample is also the proportion of marked individuals in the population. So with a very simple rule of 3, and I reorganize the equation just below, then you can get an unbiased estimate of true population size on the site with only 2 visits and marked individuals. So this way of formulating, estimating the true population size with 2 visits and marked individuals on the site is called the Lincoln-Petersen index, and is a method that is 1 century old. We can also look at another way to write this Lincoln-Petersen index. So here I show you something that we call the capture histories. The capture histories is for each individual, we can use the 1 when an individual is detected and 0 when is not detected. And then we can say that, for instance, an individual captured at the first session as 1 in the first column, and then an individual that was missed at the second session as 0 in the column. So here we are N10. This is the number of individuals that have been captured at the first session and missed at the second session. So this is the number of individuals that we could capture only at the first session. So we can write the equation for this number of individuals. This number of individuals is the number of individuals in the population, the true population size, multiplied by something that we call P1, the capture probability at the first session, multiplied by the complementary of the capture probability at P2. What does it mean? It means that here you have a 0, the individuals were present because the population is closed, but we missed these individuals. So it means that we have a capture probability at the second session, but we will not P2. And this is the complementary of the probability. So the probability to miss 1 individual is written by 1 minus P2. So the number of individuals that exhibit this capture history, 1 and then 0, is the number of individuals in the population multiplied by 2 quantities, P1, capture probability at the first session, and 1 minus P2, the capture probability at the second session. So you can see here that we have a multiplication. The multiplication implies in statistics that the 2 probabilities are independent. So it goes back to the assumption that the capture probability does not, at the second session, does not depend on the capture probability at the first session. So we can do that also for the other capture history, for the individuals that were missed at the first session and detected for the first time at the second session. And the rationale is exactly the same. We have a number of individuals in the population. We miss the individual at the first session, so 1 minus P1, and we multiply that by the fact that we detected this individual at the second session, P2. And then we also have the number of individuals detected at the 2 sessions, 1 and 1. It is the number of individuals available in the population. multiplied by the probability to capture them at the first session and to capture them at the second session. So we have three equations. We have three unknown values, n, p1, and p2. So there is no difficulties. We can reorganize this equation to get an estimate of n given the number of individuals in each category, in each type of capture histories. So I did that just here. So if we rearrange this equation, we can have an estimate of n that is given by the number of individuals with a capture history 1, 0, plus the number of individuals with a history 0, 1, plus the number of individuals with a history n, 1, 1, meaning here that it's the number of individuals detected at least once. And then we have a combination of detection probability, 1 minus p1, meaning that the probability to miss the individual at the first session, multiplied by y minus p2, the probability to be missed at the second capture, sorry, and then the multiplication of that is the probability to miss twice the individuals. And then if we take the complementary of that, 1 minus this probability, it is the probability to be captured at least once. We can call that P star. It is very common in capture-recapture literature. And then we have an estimate of n given by the number of individual captured at least once divided by the probability to capture individuals at least once. So this is very easy. And if we go back to one of the first slides of my course, remember that we formulated the population size as the combination of row count on the field divided by the detection probability. So this is exactly the same equation. We have here the number of individuals detected at least once, so the number of individuals counted, and the detection probability of the individuals. So the capture-recapture allows to estimate these parameters as we did, as we wanted, as I show you in the introduction. So this method of Lincoln-Peterson index, as I told you just before, is not new. It was developed by a guy, a statistician called Peterson, that was working on fish, and then developed a bit more by Lincoln, formulated a bit more by Lincoln, that was working on birds. And this method is 1 century years old. So this is very basic, but it works. And you can get, with only 2 visits on the field, an estimate of your population size. So this method, it comes with some assumption. First, it usually implies some marking of individuals. You have to recognize the individuals that have been captured at the first session when you conduct the second session. But it's not necessary to have individual identification. You can have also only group marking. So how do we mark individuals? There is a lot of techniques to mark individuals in the field. So you can add some physical alteration of individuals, such as here for this seal. You can make a scratch on the carapace of tortoise, and you can kit hairs on big mammals or small mammals, for instance. Of course, you all know that we can add some marks. So you have here the classical Darvik rings on birds, or ear tags in some mammals, or rings in the beak and nose for birds, and you can add some dots on some individuals. And sometimes you don't need to add some marks. You can recognize the individuals with natural marks, for instance, injuries in cetacean, or tigers that have tigers or amphibians that have individual pattern of coloration. And you can also now use genetic analysis, DNA sampling, through faces or hairs or stuff like that, to identify individuals, for instance, using microsatellite to recognize the individuals when you go in the field. Okay, so that was the first assumption. Individuals have to be recognized, to be marked. The second assumption, very important assumption that I told you just before, is that the population is close demographically and geographically. And I will explain that with a very simple example with a population that is not close geographically. So let's say that we have a sampling area, a study area that is the blue circle here, that hosts 10 individuals at the beginning, at the first session we conduct on the field. Let's say that we are very, very, very efficient and that we capture 100% of the individuals that are present in the study area. So there is 10 individuals and we capture and mark 10 individuals and we release them on the field. But you can see here that we have red dots, and these red dots are individuals that are outside the study area. So these individuals, we do not capture them because they are occupying at the time where we conduct the fieldwork, they are occupying a zone that is outside our study area. But if this species has movement capabilities, dispersal capabilities, we can, of course, have individuals that goes out, that leave out the study area, and then individuals that enter the study area between different field sessions. So we go back later in this study area, let's say 1 month later, and then we still have 10 individuals in the study area, but in these 10 individuals, we have some individuals that were already present at the first session and some individuals that were outside the study area at the first session. We have a mix of individuals that were present at the first session and absent at the first session. So we go in the field, we capture some individuals. Again, let's say that we are very efficient and we capture 100% of the individuals. And we capture 10 individuals, among which only 3 individuals are already marked. So we can use the Lincoln-Peter subindex, and then we've got an estimate of a population size that is 30 individuals, while we had 10 individuals at the first session and 10 individuals at the second session. So we have a huge bias in the population size estimation. We overestimate a lot the population size. So as soon as the closure assumption is not fulfilled, you have overestimation of population size. So here we estimate some kind of supra-population, including the study area, the buffer around the study area. But this is only true if the individual move randomly. And this is very, very rare in ecology and population ecology. So we have an estimate of population size, but we cannot that is not very useful because we can't make inference on the surface we are sampling. So the closure assumption is crucial in capture-recapture. We have some more assumptions. We have the assumption that all individuals are equally likely to be caught in the sample area. This is why we use only 1 detection probability at the first session and 1 detection probability at the second session, meaning that all the individuals are the same detection probability. We'll go back a bit later on this assumption. And then we have a third assumption that is crucial too, that the individuals, they do not lose their mark, or that the mark are not unobserved. Why this is very important? This is very important because if individuals lose their mark and then you recapture them at the second session without their mark, you consider that they are newly captured individuals, and then it leads to an overestimation of a population size because you underestimate the number of individuals that have been already captured at the first session. Okay, so this is the assumption. Let's go back to the second assumption here. Individuals are equally likely to be caught in each sample. So it means that all individuals have the same capture probability. This is a very strong assumption because we know, and we discussed about that just a bit earlier, that the detection probability changes a lot over time and over space. So we know that, for instance, detection probability can vary over time because of weather, I told you this morning, or because of sampling effort that can vary depending on the day, because you have some constraint in the field. So this is not individual variation in capture-recapture, but mainly temporal variation of capture-recapture. But we have sometimes some individual heterogeneity in capture-recapture variation of capture probability. For instance, we can have something that we call the behavioral response to capture, or trap dependence. It's the phenomena where individuals that have been already captured have not the same recapture probability than the naive individuals. So it occurs, for instance, when individuals are traumatized, are stressed by the capture. And then when you go back in the field the second time, these individuals that have already experienced a capture, they try to avoid, they are better at avoiding the trap of the observer because they have been stressed by the first capture. And we can have also something that we call individual heterogeneity, meaning that all individuals have different capture probability because of age difference, sex difference, or social status difference. And we can, of course, have a combination of these different effects. So the Lincoln-Peterson index, you can see that there is a lot of assumptions that are very, very constraining. And we cannot accommodate for source of variation in capture-recapture with the Lincoln-Peterson index. We have to assume that there is no variation of capture-recapture except eventually time variation in capture-recapture and capture probability. So to test the potential existence of this effect and to take them into account to get unbiased estimate of population size, we need more. So let's go with more fieldwork. We have the budget to do session here, 4 sessions, and we can go back to the capture history I told you a bit earlier. So we have some potential capture history that we can write here with one line is one row is a capture history and one column is one line is an individual, and one column is a field session. We use a 1 when we capture individuals and 0 when we missed the individual of this session. We are still in closed population, so individuals are present from the first session to the last session in the study area, meaning that when we have a 0, this is the first capture history in this table is an individual that has been seen captured at the first session, missed at the second session, seen at the third session, and seen at the fourth session. We can do that for all different types of capture history and have a full table for all the individuals we capture in the field with their estimate of an unbiased estimate of population size. We have still to rely on the assumption that the population is closed demographically and geographically for the same reason that I explained you with a small slide with a study area open and individuals that come in and come out and leave out. We have for the Lincoln-Peterson index that individuals do not lose their mark for the same reason than for the Lincoln-Peterson index. And we also have the assumption that all individuals are equally likely to be caught in each sample. So this is exactly the same true assumption but for the Lincoln-Peterson index. So we'll write a first model with this assumption and we'll see how we this capture the first session, capture the second session, and to be captured first session. And individuals can have different capture history. For instance, here, these individuals, they were not captured the first sessions. So 1 minus P, probability to miss the individuals, complementary to the probability to capture the individuals. Possibilities 0, 0, 0 goal that we missed at the 3 in our dataset. And the goal of a method in capture-recapture will be to estimate the number of individuals that we missed in the when we go in the field. So story 111, 110, you should get with this value of P and N and compare this number to the observed number of histories in your dataset. Then he modified a bit the value of P and N, change a bit this value and do the same calculation and try to find the value of P and N that will lead to the closest match between the number of history in each categories that you predict with this value of P and N and that you have eventually in your dataset. So this is an algorithm that allows to get the best estimate of N and P given your dataset. Okay, so here we just speak about the M0 model. This is a model that is very, very constrained, and we would like to relax some assumption. Notably, we would like to add some time variation in detection probability because this is something that is very, very common on the field, notably because the activity, the phenology of the weather, or the experience of the observer change over time. And we would like also to build a model that we'll call MB, that is a model where the capture and the recapture probability can be different, something that we call trap dependence. But I see that it's 9:50, so we will have a short break, 10 minutes break. We'll go back at 10 and we'll continue with this model at 10. See you soon. Okay, hi again, I'm back. So just 1 minute, we'll wait for 1 minute that people are connect and then we go. I see that there is 2 questions in the the chat, the helper, they will come back and respond to this question very soon, I think. So let's go to the course. So we were just finishing the previous session with the M0 model, where the detection probability, the capture probability, is constant over time over individuals. And we were speaking about trying to fit some more complex model to get unbiased estimates of population size when there is time variation of detection probability or individual detection, individual heterogeneity in detection probability. So let's begin with the time variation. So the capture probabilities, they can, of course, vary with session because of weather condition, field effort, observer experience, and so on. So let's say that we have a K session. If we have K session, we have K plus 1 parameters to estimate. We have one detection probability or capture probability for each session to estimate, and of course, the population size we are interested in. So we can go back to our capture history and try to write the capture probability, the probability associated to each capture history. The capture histories are still the same. It's just that we will fit a more complex model on the same dataset. So here, the individuals that have been captured at all three sessions in the field, they have a probability of P1 multiplied by P2 multiplied by P3. So here we have one capture probability for the first session, one capture probability for the second session called P2, and one capture probability for the third session called P3. So we have three different capture probabilities to estimate. We can go to the other history. So the second one, for instance, 110 detected at the first session, at the second session, and missed at the third session. We have the capture probability to be captured, the probability to be captured at the first session multiplied by the probability to be captured at the second session, and then the complementary of the capture probability at the first session, 1 minus P3. And we also have the probability to be missed at the free session by the multiplication of the free complementary of the free capture probability for each session. So we can write this equation as we did before. As we did before, we have the number of individuals in each capture history, and we can reorganize the equation to get an estimate of the true population size and P1, P2, and P3. Of course, again, we won't do that by algebra. We'll use the maximum likelihood, so as I told you for the M0 model, and the maximum likelihood will provide, we return an estimate of N, P1, P2, and P3 that are the best estimates given the dataset you have collected in the field. So let's move to another model, the MB model. The MB model is a model where we assume that the individual, they respond to the first capture. So it means that the capture probability differs from the recapture probability. It means that the individuals that have already experienced a capture, they have not the same capture probability that the naive individuals. So we have two types of behavioral response that we also call trap dependence. We have trap shy individuals. Trap shy means that the individuals that have already been captured have a lower recapture probability than naive individuals. So we'll call P the capture probability and C the recapture probability. So in situation where we have trap shyness, C is lower than P. So I explained you just a bit earlier that it can be in the situation where an individual is stressed, individuals are stressed by the capture and then avoid the trap of the observer during the successive sessions. But we can also have some situation where we have trap happiness, where the recapture probability is higher than the capture probability. The typical situation that generates some trap happiness is when you always go on the same spot in the field because you know that you have already marked individuals in this spot, and then you capture always the same individuals, and you miss a lot of individuals that are occupying area that you do not prospect. So in this model, we have three parameters to estimate: N, P, the capture probability, and C, the recapture probability. So we can go back to capture history and write the probability associated to each capture history. So for 111, it means that the individual has been captured at the first session, and then recapture at the second session, and then recapture at the third session. So we have P, the probability to be captured at the first session, multiplied by the recapture probability at the second session, and the recapture probability at the third session. So to illustrate that a bit more, we have here a situation where the individuals have not been captured at the first session and then captured at the second and third session. So it has not been captured at the first session, so the probability is y minus p. At the second session, it is captured, but it was not captured before. So it is a naive individual, so it is with the probability p. And then at the first session, these individuals have already been captured, so we use the recapture probability because the individual is not naive anymore. So we can, again, write all the equation associated to the number of individuals in each capture history and use the maximum likelihood to get an estimate of n, the true population size, p and c, that provide the best match between the predicted number of history and the observed number of history you have in your dataset. So here we have 3 different models to fit to the same dataset that are more or less complex. I will show you a last model that is a model with individual heterogeneity of capture. So the capture probability can depend on several unknown variables on the field, the age, the sex, the social status, etc. For instance, it's much more easier to capture a very aggressive male of iguana, for instance, because it will be easy to detect, while it will be very difficult to capture very discrete females or very discrete juveniles. So when you capture an individual, if you don't know why it states, you might not know if it's very easy to capture or not. So we have unknown variables that can explain the capture probability of the individuals. So each individual has a unique capture probability. If we try to write a model like that, we will have n+1 parameters. So it means that we have the true population size plus 1 capture probability for each individual. And of course, when we try to do that, we have too many parameters for the dataset we have. So we can't estimate 1 capture probability for each individual when we have capture heterogeneity. So a few years ago, Shirley Pledger, a statistician, she developed a tricky model to estimate capture-recapture probability with heterogeneity using something called the mixture model. So the mixture model assumes that individuals in the population belongs to 2 groups with different capture probabilities. We have a proportion pi of individuals in the population that belongs to the first group of capture probability, but maybe the highest capture probability, pH. And we have a proportion 1 minus pi, the complementary of pi, to belong to the second group that will exhibit a low capture probability that we note here, PL. Then the mean detection probability in the population is given by pi multiplied by pH plus 1 minus pi multiplied by PL. So we can go back to our capture history, and for each individual, we can write, replace the P by this equation combining 2 components, the probability to belong to one group and the probability, the capture probability associated to this group. And then we can use these parameters and this dataset to use maximum likelihood, and then the maximum likelihood will return 4 parameters: the population size unbiased by the capture heterogeneity, the proportion of individuals that belongs to one of the groups, and the capture-recapture probability associated to each group. So this is a tricky model that is very efficient in dealing with capture heterogeneity. So here, this is a very simple example with 2 groups, but of course we can develop that for more than 2 groups of heterogeneity if we suspect that we have more than 2 groups of individuals with different capture probability. Okay, so we have now 4 models, M0, MT, MB, MH. And of course, we can combine these different effects because in some situation, in some field situation, we can have a combination of trial dependence and time variation of capture probability, or trial dependence and heterogeneity among individuals, and so on. So we can build more complex model by the combination of the different effects we saw just before, and there is no specific difficulties. We just have to write the capture history as we did just before, and use the maximum likelihood to get an estimate of the different parameters we are interested on. We can also use some individual covariates, such as age, sex, body condition, or something like that, something that we know that may affect the capture probability, and use in the modeling. I will not develop here that, but I will show you a small example with a sex effect during the live demo just after. But Olivier will explain you this afternoon with open population how we deal with this kind of covariate concretely in the formulation of the probability associated to capture histories. Okay, so before going to the live demo, 2 or 3 more thoughts on what can we do with a dataset of capture collected in the field. Here we saw that we can fit several models, maybe 8 models or 9 models, with a different combination of effects regarding the time, the individual heterogeneity, or stuff like that. And we can fit all these models very easily on our dataset. Each model will return a different population size estimate. And of course, we have then to decide what is the best model for our dataset. So we can decide by expert judgment, considering that we know that there is time variation or individual heterogeneity, but we can also rely on some statistical tools to select the best model that fits the data. So how can we do that? We know in statistics that the more complex are the models, usually the more they explain the data. A more complex model with more parameters, more covariates, will explain much more variance than a very simple model. So the more complex models are always the model that explain the largest part of the variance in the dataset. Yet sometimes the complexification of a model leads to only very small improvement of the percentage of explained variance. So we can have a discussion about, is it necessary to complexify the model if we only improve just a little bit the percentage of explained variance? So the idea in ecology and in a lot of different fields in statistics, using statistics, is that we will penalize model with too many parameters to be as parsimonious as possible. To do that, when we use the maximum likelihood, we can use a criterion called the Akaike Information Criterion, AIC. That is a tool developed by a Japanese mathematician back in the 70s. So the AIC criterion is made of 2 components, the deviance and the number of parameters of the model. So the deviance, just to explain you very shortly, briefly, is a measure of the unexplained variance of a model. It's the part that the model do not explain in the variance of the data. So when the model explain well the data set, then the deviance is low, and when the model fit less the data set, the deviance is high. K here is the number of parameters in the model. And so if you look at the equation of the AIC, deviance plus 2 times the number of parameters, then you can see that it's a balance between the quality of fit of the model, the percentage of deviance explained, and the complexity of the model. When for each model that you will fit with the maximum likelihood, you will get an AIC, and then you can select the model with the lowest AIC. The model with the lowest AIC will be the model that explains the most the data with the less parameters. So this is a criterion of parsimony. Okay, last thought on capture-recapture dataset and modeling for closed population. A very, very important assumption I told you is the closure assumption. We've got some test, statistical test to test this closure assumption. That is a kind of a goodness of fit test to verify that the model we use adequately fit the type of data we have. And so we have different type of tests, notably two pretty old tests, the test of Otis and the test of Stanley and Berman. These tests, they are available in R, notably in a package made for spatial capture-recapture. But we know by the literature and some simulation that these tests are very sensitive to oversource or variation, such as capture heterogeneity. Notably, when you have some capture heterogeneity, the closure test usually say that the population is open, even if it is closed. And we also know that these tests, they perform very low, their performance is very low when the capture history, when the detection, the capture probability is low, because we have a lot of zero in the capture history, and then these tests perform poorly when there is a lot of zero in the detection, in the capture history. So you can use this test, but this is now relatively controversial. And as a ecologist and statistician in ecology, I suggest to rely more on an ecological justification. So to rely more on building a relevant sampling design, for instance, by choosing a site that is relatively close to for the population, but also working with very close with a field session at very short intervals, rather than using statistical tests that sometimes will say that the population is open while it is closed. Okay, so here are a few references that you can that I cited in this first lecture, and further reading. So here are two documents that you can read. First, the Bible I was telling you just before, when you can find a lot of mathematical formulation, very detailed formulation for the capture-recapture for closed population, but also open population. And another document that you will find on the FIDOT website for the pages of Mark software. Mark is a software dedicated to the analysis of capture-recapture. And then if you go to this page, you can download a document called a Gentle Introduction to Mark. This is a manual for Mark software, but it's also developed with a very, very didactic approach, the different model that you can use with Mark, and you have a lot of very nice material to understand, to look at for capture-recapture for closed population. So now I will make a short demonstration on how to fit capture-recapture model for closed population in R. So I have to switch my screen. Okay. Okay, so you can find all this material on the website, and you have a script that you can download on the website. And here is only slide, and I will go through the script with different slides. So to analyze capture data for closed population, we'll use a library, a package called RMark. So RMark is a package dedicated to analysis of capture-recapture data. But it is important to know that RMark is not a package that fit the model, that use the maximum likelihood to fit the model. It's a package that prepares the data and use the Mark software in the background to fit the model. So you need to use this package, you need to install Mark, and then you prepare all the stuff in R, but in the background, you see nothing, but in the background, RMark will use the optimization process, the maximum likelihood process from Mark. So you will do everything on R, but you have to install mark in your computer. So on the website, you can download a dataset called mouse.inp. That is, as the name is very clear, on a mouse. You can inspect the first line of the dataset. You can open it with a text pad, for instance. And here we'll use a function from the RMark library called convert.inp. That is a function that opens the INP format from the data format of a file. The INP format is the classical format for people working in a capture-recapture. So it's the format used, for instance, for Mark, but also for other software like mSearch or eSearch. So you have your data set in this classical format for capture-recapture data, and you can convert it to be used by RMark using this convert.inp and store this dataset in an object that I call here mouse. We can have a quick look to this dataset. This dataset is made of capture histories. Each row is a capture history. So for instance, here you have an individual that have been captured at the first session and then missed at the next 3 sessions. So this is a dataset. We are 4 field sessions. And you have a second column in this dataset that is called FREQ for frequency. And this is the number of individuals in the line. So here we have 1 individual per line, per row, with each individual with his own capture history. We can have a quick look to the size of the dataset, notably the number of individuals that will be given by the number of lines in the dataset, and here we have 82 individuals. So just with a quick look to the dataset, we can already see that the detection probability, the capture probability, is probably very low because we have a lot of zero in the capture histories. Okay, so to get an estimate of population size for closed population with RMark, we need 3 steps. We need to prepare the data for RMark. We need to define the different models we want to fit. We just saw that we have a lot of different models we can fit. And then we have to fit the model that will be done using the calculation, the core of calculation of Mark software. And then we can explore the result in R. So to prepare the data, we relied on 2 different functions. The process.data, that is a function that will specify to RMark the type of model we would like to fit and the data set we have. So this function will take as argument the data set, here the mouse object that we built with the convert.inp function. It will use an argument called begin.time, that is at which session we would like the capture probability to be used. So here we like to use the 4 field session. So we say that we begin at the first session. And then a very important argument is that the model argument. Here we specify full heterogeneity. Full heterogeneity, the model here is the type of model we would like to fit with Mark. Mark, it can fit a lot of different type of models. Of course, here we are working with closed population model, but it can fit open population model, but also site occupancy model or stuff like that. So we have to specify to Mark what kind of model we will use on this dataset. So here, full heterogeneity, full het, refers to the most complex model form of closed population, for closed population. And of course, because this is the most complex form, we can use this type of model to fit simpler model by putting some constraint on the parameter we will use. And I will show you that just after. So here we have 2 functions that will allow to prepare the data. The first to prepare the data set and say to specify to RMark what kind of model we like to do. And then a second function called make.design.data That is a bit tricky. That is a very function for a very complex thing in statistics. It's a function that builds something called a matrix design, and the matrix design is an information that will need mark and R mark to know the number of parameters to estimate and their structure. So you don't need to understand much more than that, but you have to prepare this matrix design using this function and using the type of model and the type of dataset you have informed using the process.data. So two functions, and now you have prepared the dataset and specify to R mark what type of model and what type of type of model you want to fit in the data. Then we have to define the models we want to fit. Here, when I say define, it's not the type of model, but this is the model, each model we want to fit. For example, M0 or MB or MT. So we'll use to do that, we'll use a function that will do three different things in a single function. We'll specify the effect we want in the model. We'll create a list of all the models we want to fit. And then we will prepare all these specific model for mark. And then we will launch R mark that will fit all these different models. Okay, so this is the function. It's a bit long function, but this is very simple. We have three different steps. We prepare here the model we want to fit. We build a list with this model, and we prepare this list of models to send to mark. So how do we specify the effect we want to add in the model? To do that, we use a list, the format list, and then we specify with the formula the type of effect we want in the model. So when the formula is specified like that, ~1, it means that we don't want to add any effect on the capture probability. The one means constant. So we'll have a constant capture probability. It is important to note that by default, in R mark and in R, if you do not specify that you want to have P and C, so the capture and the recapture probability equal, then it will fit a model where P and C are different. So we have to specify here that if we want a constant model, the M0 model, we don't want any effect on P, but we also want P and C to be equal. And to do that, we have to use the argument share equal true. By default, the share equal false, and then if it marks fit a model where P and C differ. So this is the first model. This is the M0 model. The constant, no effect on the P, and P and C equal. And we can call this model P dot. You can choose another name, of course, if you want. We can make a second model that we'll call P dot behave. So this is the model MB. We would like to have capture and recapture that differ. And to do that, we keep formula ~1, no effect on P, but we remove the argument share equal true, then share will be false and P and C will differ. So this is the MB model. We can continue like that. For instance, if we want to add a time effect on the capture probability, we can build a model that we call P.time, and the formula will specify that we want a time effect. So it's very easy to write. We just have to add the time argument in the formula, and then we'll have a time effect. And if we specify share equal true, then we have P and C equal. And we can build like that a list of model, time variation, capture and recapture equal or different, and heterogeneity that we can specify using the term mixture because it relates to the Pledger mixture model. So here we prepare 8 different models that are a combination of effects on the capture probability, time effect, heterogeneity, but also time and heterogeneity together. And then all these models, we can gather them in a single object that we'll call here mouse.model.list using the function create.model.list. This function, it will scan the local environment of R and detect all the object that looks like a model for closed population and gather all this model in a single object, single list of objects. So this is the second step. And the first step is to prepare the list of model to send to Mark. And for that, we need to provide to Mark some different information. We need to provide the list of model we want to fit. We need to provide the data set we have to fit, on which we want to fit this model. And we need to provide the design matrix that we built for Mark. And then with this function, everything is prepared to be sent to Mark. And then we can add this line of code at the end to get the result of this function when Mark finish the fitting of different models. So we can use this function and launch all the fitting of all the 8 model or 9 model, I don't remember, that we list in the previous function. On R, you will have a lot of message that will appear because when Mark fit the model, he return a lot of information, which is not very important. But at the end, we will have an object called mouse.result that will store all the results of a different fitting. So we'll check in this object the information we are interested in. Okay, so let's say that we fitted the models with Mark, and then so you have nothing to do. You just have to run the function, and Mark will work in the background, but you just have to work on R. So now we can have a look to the result of the fitting. And to do that, we can print the result of mouse.results object. When you type mouse.result, it will print a table with the different model and the AIC. Each line is a model. You have a name of a model that is not very explicit, but I will come back a bit later on that. You have a number of parameters in the model, and you have the AIC of the model. And these models, they are ordered by increasing AIC. So to understand what model is on what line, you can try to understand this code here, that I will explain you a bit later how to read it, or you can rely on the first column here, that is the ID of the model. And if you type this line of code, names mouse.result, then you have the name of the model you use in the function and their ID just before. Okay, so how do we interpret these different information, and notably what we have on this model? So we have 1, 2, 3, 4 parameters to fit. We have the pi parameter. So if you remember, the pi parameter was the probability to belong to one group of heterogeneity. And here we have tilde1, meaning that we have no effect on this pi. So we have no heterogeneity. We have a p, that is the capture probability, with tilde1, meaning we have a constant capture probability. We have c with tilde1, c being the recapture probability. So we have no effect on the recapture probability. And we have f0, that is a new parameter that we did not discuss before, that is tilde1, so that is constant. So f0 is the number of individuals that have been missed during the field session. So this is the number of individuals we try to estimate to get the entire population size, the full population size, by the sum of f0 and the number of individuals that we had captured at least once in the field. So Mark, when he estimate population size for closed population, it does not try to estimate the population size. It tries to estimate the number of individuals that we missed, the individuals that the 000 capture history, for instance, and then to add them, this number, to the number of individuals that we've captured at least once in the field. So this model is a model where we have no capture heterogeneity because pi is still 1. We have a capture probability that is constant, a recapture probability that is constant, and a constant number of missed individuals. We can check all the models like that. For instance, the second model is one model with no capture heterogeneity, an effect of time on the capture probability, and no effect on the recapture probability, and so on. And here on the line where the ID is 7, you have something new. You have a C with brackets, with nothing in the bracket. And when there is nothing in the bracket for C, it means that C and P are strictly equal. So here, C has the same value of P, and so the same effect than P. Okay, so here we have our list of 8 models we fitted. And the best model here is a model where, best model in terms of AIC, is a model where we have no heterogeneity of capture among individuals, between individuals, a recapture probability constant, a capture probability constant, and a recapture probability constant that differ from the capture probability. Okay, we can go now to check the estimates provided by Mark, because this is the most important thing. We have to look at the biology now and get the estimates of a model we would like to check. So for instance, if we would like to have the estimates of the constant model, the first model we list in the list of model we fitted in the function I showed you just before, the p dot. We can check inside the mouse dot result using a dollar to get the result of a p dot result, to add a dollar to check the result of this object, and to add a dollar to check the real parameters of this object. So real means that this is the estimate provided by the maximum likelihood. So here when you check this object, this part of the object, you print it, and then you have 3 different lines. The first line is the pi, the proportion of individuals that belongs to one group of capture heterogeneity. And because we fit a constant model, these parameters has no interest. Here it is estimated to 0.5, but you can see that the standard error is 0, meaning that this parameter is not estimated. It's not estimated because we do not ask for heterogeneity. So we can just skip these parameters. Then we have 2 other parameters, the P, the capture probability, that is here equal to the recapture probability, because we specify that P and C should be equal with a share equal true option. And we have the estimation of this capture probability that is 0.23. So this is relatively low, as we suspected it when we look at the capture histories. And we have the F0, the number of individuals that we missed during the 3 sessions in the field, that is estimated to 46 individuals. Then we can check at the population size. The population size is not directly estimated using the closed population model in Mark, because Mark estimates the number of missed individuals and add it to the number of capture individuals. So this is a derived parameter. So we can use this line of code. $, we check the model we are interested in, the result of this model, and the derived parameters of this model. And then you get here the population size, the true population size estimated to 128 individuals. And if you remember, we had 82 lines in our dataset, so 82 individuals captured at least once, and 46 individuals estimated as missed by the fitting of the model. So it leads to 128 individuals in the population size. And of course, you have the 95% confidence interval of the estimation. Okay, so just to finish with capture-recapture, I will just show you a very short example for a data set where we have two groups of individuals. So it will still be on a mouse, and we'll have male and female, and we know that the individual is a male or a female. So you can check the data set on the website and download it. It's called mouse_groups.inp. You will have in this file different information. You will have the capture histories, as we did before, and you will have two more columns. And these two columns, they contain values 0 or 1, and they correspond to the sex of the individual. So in the classical format for capture-recapture models, the INP format, we do not use letters to specify the groups. We have to use something called the dummy variable. And the dummy variables is how to code for discrete variables using different modalities. Each column will correspond to modalities of categorical variable, male and female here. And when the individual is a male, we put a 1 in the column of male and a 0 in the column of female. And when the individual is a female, we put a 1 in the column of female and a 0 in the column of male. So it's a way to code for categorical variables using only a value of 0 and 1. So we open this dataset and we convert it for Hallmark using the convert.inp as we did before. Now we have more arguments to provide. Notably, there is these two columns with 1 and 0 that correspond to the sex. And we have to specify to mark that these two columns are information on groups and name these two groups for Hallmark. And we have to specify that we have no other covariates. The two columns are just one covariate for sex, one information of group, and not an individual covariate. So if we look at the object that we build with, we store in this mouse object from the convert.inp function, we have the same type of file than before. We have each line is one individual. The frequency is 1 for each line. We have a capture history, so we have still 4 field sessions here. And we now have one more column that is the sex. And in R, we can manipulate easily text. So we have a letter for the sex. So here a quick look at the first row of the data. It seems that the capture probability is a bit lower, a bit higher than the dataset we used before, because we have far less 0 in this first capture histories than that we have in the previous dataset. And then we'll do exactly the same process as before. We'll prepare the data with a process.data function. We just now have to provide more information to our mark that we have some groups. So we have to add an argument groups equal sex, and then make the matrix design using the mouse.proc object as we did before. Then we can prepare different model to fit. So we can fit exactly the same model as before. Of course, we now have information of the sex, but we can also fit simpler model without the sex information. So you have here the first line are exactly 8 models we fit on the previous dataset. So this is model where we have no information. We consider we have no information of sex or no effect of sex on capture or recapture probability. But we also add here an example with one more model that includes the sex as a covariate on the capture probability by using tilde-sex and recapture probability by using tilde-sex. And as we do not add the option share, then P and C will differ. We create the model list of all these 9 models we prepare. We prepare with the mark.wrapper function the model list, the data, and the matrix design. We send that to Mark, and then Mark fit all the model in the background and print a lot of different stuff as before. And then we've got the mouse dot results. That is, as before, the table of all the different models fitted in Mark with their name, their ID, their name, their number of parameters, and their AIC by increasing order by increasing value. So here we can see that the first model is the model with the sex effect that we added to the list of the previous model. And so we have pi till 1, no capture heterogeneity, p till sex, an effect of sex on capture, c till sex, an effect of sex of recapture, and f0 constant. So this is the best model, meaning that we have different capture probability between the sexes. So we can check the detail of this result by looking at the estimates of the parameters. That's what we are interested in, the biology. And we still have, so this is the same type of line of code than before, except change the name of the model we like to check. The first line is the pi estimate. Again, it's a model without heterogeneity, so this pi is not relevant to look at. Then we have two lines for the p. We have two lines because we ask a model with two values, one values for each, two estimates, one estimate for each sex. So we have the estimate for the female group F and the estimate for the male group M. So we can see that the female has a capture probability of about 60% and the male of about 50%. So meaning here that the female are easier to capture than male, slightly easier to capture than male. And then we have two lines for recapture probability because we do not specify the share equal true option in this model. And so the recapture probability for female is 0.4 and for male is 0.22. So we still have a difference of recapture probability between males and female, females being higher, easier to recapture than males, but we also have a relatively strong difference of between capture probability and recapture probability, individuals being harder to capture when they are not naive, when they have been captured at the previous session. Okay, so we can look at the derive. Okay, so just we have also the F0 here. This is the number of missed individuals, each for male and female. So it's two individuals, about two individuals in male and female. So you can see that it's much lower than what we have in the previous dataset where it was about 45 individuals. And this is much lower because the capture probability is much higher. So it means that we capture, with 4 sessions, we capture much more individuals in the population than when we have a low recapture probability. In the previous dataset, it was about 20% of our capture probability. That was pretty low. And we can check out the derived parameters using the same type of line of code than before. And we have now an estimate of population size for females and for males. So that's it for the live demo of Capture-recapture. So we'll make a break. We are right on time. We'll make 10 minutes break, and then we'll go back at 11 for a lecture on distance sampling method. See you very soon. Okay, so let's go back to the course. We'll now speak about another method to deal with detection issue in the field to estimate population size or abundances or densities. That is called distance sampling. So if we go back to the traditional methods to estimate population size or densities, we go in the field, we define the transect. We usually define a width on which we think that we have 100% of detection, and we count animals or plants along this transect of fixed width. Here, for instance, we have 5 birds, and we count these 5 birds. We can do also the same approach with a fixed point that we call a circular plot with a fixed surface, and we'll count all individuals in the area. Here, 5 birds also. Using this row counts in the sample, in the strip, we can easily estimate the density of animals or plants by this small equation that is a bit of full, but very easy to understand. We have an estimate of the density D that is provided by the summation of the different counts Y here for each plot, each strip transect or each circular plot from circular plot 1 to n. So we make the sum of the different counts on the different sample units. Very easy. And then we divided these counts by the surface of the different plots, the sum of the surface we sample. We can translate that into abundance by using an estimate of the abundance or the population size is given by the counts divided by the surface, the proportion of the study area that we eventually sample with the plots or the strips. So a very simple example with line transect. We have a transect or line of length L and of width W. We count individuals on these transect. So the density is given by the sum of the counts divided by the sum of the surface of a strip transect. For the circular plot, we have the same. We have circular plot with a radius called W. We have the counts of animals in these circles. We've made the summation of these counts that we divided by the surface of the different sampling units. So this is the traditional way of estimating densities. But of course, this comes with assumption. The first assumption, a very strong assumption, is that all individuals in the sample area are detected and counted. So we saw during the first 3 slides of the presentation this morning that this assumption is very strong and usually not fulfilled, because detection probability is almost always below 1, whatever species we are studying. It can be birds, mammals, plants, or whatever. And the detection probability can also vary between sample units, sorry, depending on the vegetation cover, for instance, but also among even in the sample units. For instance, along a transect, you can have very dense vegetation in a part of the transect where the detection probability is very low, and then more open vegetation in another part of the transect where the detection probability will be much higher. So the detection probability is below 1 and heterogeneous between and among the different sampling units. So we have to deal with this detection issue as we did for capture-recapture. We have to deal with that when we have row counts to estimate unbiased abundance or densities. So this is the goal of a method called distance sampling. The rationale of distance sampling was formulated back to the 80s by an English statistician called Steve Buckland. And the rationale of the first idea of Steve Buckland was that the number of detection of individuals tends to decrease with the distance of to the observer. Of course, the individuals of target species that are very far from the observer, they are often much more difficult to detect because they can be masked by the vegetation, or they are simply smaller because they are further. So if the number of detection tends to decrease with the distance to the observer, it means that we have some information on the detection process in the information collected with the distance to the observer. So Steve Buckland used this idea to see if we can estimate the detection probability by recording the distances of detected individuals rather than just their presence. Not just counting them, but also recording their distance to the observer. So this leads to a very different sampling design than what we saw in the traditional approach. We can still use transect or point counts, but now we will record not only the presence of the individuals, but we will record the perpendicular distance to the transect. So if, for instance, here you have a bird, you have the observer that walks along this transect, and when the observer detects a bird, he records the perpendicular distance to the transect. The two differences with the traditional method also is that we have the distance, but we also assume, accept that we miss some individuals. For instance, this bird here was missed. So we know that we miss some individuals. And also, there is no limit to the detection area. There is not a fixed width of the transect. We can, of course, have several transects over the study area to have sample units, replicated sample units. And we can also do the same type of design for fixed point count, where the observer is at a location and record all the radial distance between the individuals and the point of observation. Again, we have some distances, not only the presence of individuals, we accept that we miss some individuals. For instance, this bird was missed. And again, we do not have a fixed radius of observation. We not all the individuals we detect, whatever the distance. We can, of course, here again, have several point location to get some spatial replication. So if we remember the very first slides, we had a slide where I told you that the population size was provided by the number of detected individuals divided by the detection probability of these individuals. So here, if we formulate that for densities, the density is given by the summation of the different counts we get on the different sampling music divided by the estimated detection probability. So the question now is, how do we estimate P, this detection probability, using the distance data collected in the field? So when you perform distance sampling method in the field, you typically have this kind of data set. You have here an histogram of the number of individuals detected in different classes of distance to the observer. This histogram is typically decreasing because we think we can assume, reasonably assume that the detection is lower when the individuals are very far from the observer than they are close to the observer. So we have a typical histogram collected in the field with distance sampling method. If the detection probability was equal to 1, perfect detection probability, then the histogram would be flat and we would have the exact same number of individuals in all the different classes. So the decrease results from the decrease in detection probability with the distance. So the rationale behind the distance sampling approach is that if we can fit a curve here, the curve is the line that separates, that split the blank, the white area and the yellow area. If we can fit a function on the histogram, then what is below the histogram is the number of individuals detected, and what is above the histogram, limited by this rectangle, is the individual that we do not detect. So the integral here, the number of individuals below, provides some information on the detection probability. For instance, a very simple example, if we go on the field and we detect 100 individuals, and that we know that this proportion below the line, the yellow area, is made of 60% of individuals of a full rectangle, then we know that the detection probability is 0.7, and then we can get an estimate of population size, unbiased estimate of population size. So the goal now is to fit a curve, a function, to the raw data, to the raw distances collected in the field to get an estimate of P. So here, for example, we have a function that we fit to the data. So what do we know? To get an estimate of P, we can get this estimate on P by using fitting a model that we call J here. J in function of y that will be noted distance to the observer. And if we perform the integral of this function that we divide it by the width of the surface area, then we can get an estimate of the detection probability. So this is the area under the curve divided by the area of the rectangle. So exactly what I tried to explain just before. So the goal will now to estimate this G function, the detection probability given the distance to the observer. And of course, G is not known. G can vary depending on the observer experience, depending on the species, and depending, of course, of the structure of the environment, notably the vegetation cover or the vegetation density, for example. So the distance sampling approach is to go for a few models for G, and this model should have good properties. So what is mean good properties? It means model robustness, shape criterion, and efficiency. I will detail that just here. So what do we call model robustness? Robustness is the things that the function that we'll use can take a variety of shapes, meaning that we can adjust, we can fit the same type of function on very different type of data. This function should also be robust to pooling. So this is very specific to distance sampling. When you go in the field, most of the time you do not have very exact measure of distance. You make some rounding, and then you have most of the time, and I will detail that a bit later again, you have to make some classes of distance, and then it's a form of pooling, and the function that we will select have to be robust to this pooling. We also have a shape criterion, meaning that we have to find some function that can present a shoulder near the transect line. So we suspect that the detection probability is pretty high over the first meters and then decrease. So we suspect that we need a function that will have a shoulder at the distance close to the observer. And the model should be efficient, meaning that it should provide precise estimates and that will use the maximum likelihood to estimate this the parameter of this function, as we did for capture-recapture, for instance. So Steve Buckland, he developed some functions specific to distance sampling, and these functions are made of two components. There is a key function that is the main function, and he suggests to use three different key functions: the uniform, the half normal, and the result rate. And I will show you this the equation of this function just later. But these functions, they are not very flexible in terms of shape, and Steve Buckland suggested to add something to add a second component to this function. Something he called the series expansion. This is a more complex equation with a cosine function or simple polynomial that allows to make the form of the shape of the function much more flexible. So here we have our data set collected in the field, and as we did for capture-recapture, we like to fit a model to get an estimate of P using this raw data collected in the field. So we can test, for instance, the first uniform function, the key function uniform. So the uniform function is very simple one. It's a function that is only a constant. There is no parameters to estimate. This is a red line here. This is a constant. So of course, this key function, the uniform, does not look very promising for fitting to distance sampling method where detection probability decrease with the distance to the observer. We can also use the second type of function that Steve Buckland suggested, the half normal. This is a normal distribution cut at its center. We have got here the equation of this function, and we have here one parameter to estimate. This is the sigma to get this function. So this sigma is a shape parameter. When you change the sigma value, you change the length of the tail and the slope of the decrease of the detection with a distance. So it allows to have some kind of flexibility in the shape of the function. We can also use a third function that is the hazard rate, and the hazard rate is pretty close to the half normal function, except that we can have a very long flat shoulder at the short distances. This function is written here, and you have now two different parameters to estimate, the sigma and the b. So we have three different key functions with a different number of parameters. We can use the dataset and the maximum likelihood to estimate the parameters. And as we did for capture-recapture, we'll have different models fitted to the same data that will provide different value of population size estimate. And we can also use the AIC value of this model to select for the best model that fit the best the data with the less parameters possible. For the hazard rate, sorry, the B parameters allow to change again the form, and you see here that it changed the slope, the slope of the decrease of detection probability with the distance. Okay, so we have these three key functions that are not so flexible to fit to distance sampling data. And if you have some experience in collecting some distance sampling data in the field, you can have very, very different forms of histogram depending on the species and the environment, notably. So Steve Buckland is suggested to complexify the models using expansion, using as a second component that makes the shape much more flexible using a cosine function or polynomial. Just a small example. You have here the data with a uniform key function, so a flat one. But if you add a cosine expansion, series expansion, you see the cosine function, then you can strongly modify the form, the shape of the function, and then get with a uniform key function and its series expansion, a much more flexible form that fit much more better the data than the key function alone. But of course, you will have more parameters to estimate, and then you will have to select for the best model using the AIC, for instance. Okay, so what are the critical assumptions we have to make when we use distance sampling modeling on this type of data to be sure that the population that we estimate are relevant? We have three main hypotheses, three main assumptions that we have to accept. First, that the individuals, the individual for the species we target, when they are on the line near the observer, they have to be detected with a probability of 100%, meaning that at the distance 0, the detection probability is 1. The individuals that we record, they also have to be detected after their initial location. And the distance we measure, of course, have to be recorded accurately. So I will detail a bit these three assumptions just after. So why is it so important to be sure that the detection probability at the distance 0 is 1? I show you here two different boxes. One where we have a detection probability of 100% at the distance 0, so it allows to trace to define this rectangle that is a number of that is the full abundance of a population. But if the detection probability is not equal to 1, it means that at the distance 0, you have an unknown proportional individual that is missed here. This is the blue line. And then if you don't know how many individuals you missed at the line, you can't estimate this number, this size of this rectangle here, and so you can't have any estimates of population size. So in this situation, when you suspect that the detection probability at the distance 0 is not 1, you can try to estimate it. For instance, using the Lincoln-Peterson index on the line, or using radio track individuals that you can know where are these individuals and see if you detect them or not. And then if you got an estimate of the distance, the probability of detection at the distance 0, then you can correct you can unbias all your estimates. You can also try to ensure that the detection probability at the distance 0 is 1. For instance, using cameras at near the line or train pointing dogs near the line. But it is controversial because in this situation, you will have the detection function will be made of two different components, two different detection functions, one with the camera of the pointing dog and the second one with the observer. And so it's not sure that you will be able to fit a relevant detection function on this type of data. And you can also use a more recent modeling approach, like distance sampling with temporary immigration, that we also call generalized distance sampling. But it will require to repeat the survey on the same sampling unit. So you will need to perform more fieldwork and so have some more budget. I will talk a bit about this method in the last part of my talk this afternoon. Second assumption of distance sampling: the animals do not move before detection. If this assumption is not fulfilled, then we know that if the individuals they move randomly, we have a positive bias in the abundance estimates. Provided that the individuals of the target species move very slowly relative to the movement of the observer on the line translate, for instance, the bias can be small and negligible. The most important problem is then the individuals, they react to the presence of an observer. So we can have two different situations. A situation where you have an avoidance of the observer. So this is very classic. The observer arrives on the site and the individuals, they move away because they are stressed by the presence of the observer. In this situation, you will have a negative biased population size estimate. In this situation, you can often detect this effect in the histogram because you will have less individual close to the observer than further, while the hypothesis in distance sampling is that the number of detected individuals is strictly decreasing. So you can have a diagnostic then to detect the problem. The reverse situation and where is when some individuals are attracted by the observer. This is much rarer than the avoidance, but it can occur. For instance, some passerine birds, they are very curious and tend to be attracted by the observer at the point count. In this situation, you will have a positive bias in the abundance because you attract individual close to the observer. And there is no way to detect that on the histogram because you will have an histogram that will show a strong decrease in the number of individuals, but that can be either because you attract the individuals or because the detection probability sharply decrease with the distance to the observer. You have no way to identify what is the cause of this strong decrease. So there is different recommendation when you have this situation. There is some recommendation in the field. So for instance, when you do point transect, you can go on your point and then to wait for 5 or 10 minutes before proceeding to the recording distance. You let the individuals forget that you are present or go back to their normal life, and then you can begin to count the individuals. When you perform line transect, you can try to look well ahead to detect the individuals before they move in response to your presence. And you have also some trick to to deal with the situation with a modeling approach, notably by pooling the first class of distances class in which you think the individual move. Okay, and the third hypothesis is that you record distance accurately. Of course, you probably all know that the humans are very, very bad at estimating distances. Of course, you can train yourself to be better at estimating distances, but it is rather difficult, and it can change with if you are tired of, and depending also of if you have some objects that provide some information on the size and the distance. So what we know about this source of bias, if you the measured distance are randomly varying around the true distance. For instance, sometimes you overestimate and sometimes you underestimate, then the estimator is fairly robust to random error, to this random error in measurement. But of course, you will lose some precision in the estimate of population size. But the modeling approach is very sensitive to extreme outliers and to running distance. So what is the rounding distance? I told you just a bit before, but I will develop a bit more here. The rounding distance is very classical in distance estimation by humans. The short distance you will make, you will record very precise distance. For instance, you can say this individual is at 1 meter, 2 meters, or 5 meters. So the precision of the measure is at the meter scale. And then when the distance is increased, the precision decrease. For instance, you will never say that this individual is 253 meters away. You will say this individual is at 200 meters or between 200 meters and 300 meters. So the width of the classes of distance increase with the distance. And this can be a problem when you use distance sampling. So if it is the case, as it is mainly the case, you have to define this class before and deal with that in the analysis by specifying to the software that you will use to fit the model that the distance were in classes. So the recommendation is to make some classes, but to make the classes explicit before going to the field, because if you do not make these classes explicit, the risk is that the classes will be very difficult to make after, depending on the observer and the way he builds his own classes. If you have outliers, meaning very long distance measures, sometimes you can remove them. Steve Buckland he shows that you can remove 5 to 10% of the largest observation without decreasing or increasing the bias without increasing the bias in the population estimation. This is because the most important information in distance sampling is the small distance where the detection probability is close to 1. If you do some heaping, some rounding, then you can use some classes and use the cut points are the measure of a class. And the most effective solution is, of course, to accurately measure the distance, for instance, using appropriate tools like tape measure or better, the laser rangefinder. But of course, it will depend a lot of type of species you are working on. If you are working on butterflies, you won't be able to use a laser rangefinder. Okay, so before going to a short live demo of how to analyze distance sampling data, I would like to share some thoughts of goodness of the test. So if you remember the capture-recapture, we discussed before of the closure assumption, but we have some tests to test for the closure assumption. This is a goodness of the test. This is a test that verify that the data you collected are fit the hypothesis of a model you use. We have the same type of goodness of the test in distance sampling, and these goodness of the test, they have to be verified to be sure that the data you have collected are adequately are adapted to the type of model you are using. So there is several diagnostics and tests that have been developed by the team of Steve Buckland to check the fit of the goodness of distance sampling models on your dataset. I won't detail them here, but we'll show some of them in the example just after. And the general principle is to verify that there is no large discrepancy between what is predicted by the model you fitted and what you have in your own data. Last slide of the lecture before the demonstration in R. How to choose between line transect and point transect. So this is a very important choice. What we know is that point transect are very relevant for population distributed in patches because it's much more easier to put a point in a patch than a transect in a patch. It's much more convenient to use when the area is difficult to access or to survey because you don't have to move too much in the survey area. And it's naturally suited for stratification. Stratification, for instance, regarding the habitat. If you suspect that the detection probability differ between the forest and the open habitats, then it's much more easier to put some points in these habitats than transect that can sometimes cross different habitat types. The line transect on the other side, they are very efficient for spatially distributed population or population at low densities, because when the density are low or when the individuals are spatially distributed, you have a very low number of individuals around the point transect. So the line transect allows to cover a much more larger area and then collect more data of distance. We know that to get good estimates of population size or relatively precise estimate of population size, we need about 60 or 100 distance to record. So if you are working on a population that is very low density, you have to cover very large surfaces. The only point that is not written on this slide is that the point transect methods are very, very, very sensitive to the assumption of distance sampling, and notably to the assumption of movement of individuals in response to the presence of an observer. I won't detail why, but you have to know that if you suspect that individuals of a target species will move in presence to the observer, you should use line transect instead of point transect. Okay, so the distance sampling method has been used on a very, very large number of situations for birds, mammals, marine mammals, terrestrial mammals, reptiles, butterflies, dead animals, burrows, nests, dead trees, plants, etc. So there is a huge literature based on these methods. And here I show you the basic of distance sampling, but the team of Steve Buckland have been have conducted an intensive work, methodological work, to relax some assumption and complexify the model to relax an assumption. So if you are interested in this method, you can read this book that will detail all the different approaches that you can use with distance sampling, notably the most complex method that allows to relax some very restrictive assumption of distance sampling approach. So now, before lunch, we'll have a very short live demo in R of distance sampling. Okay, so to do that, we will use a library called distance. This is a library that allows to fit basic model of distance sampling. Of course, if you want to fit much complex model, you will find some other libraries, other package in R. But for this introduction to the concept of distance sampling, we'll use this package that is very easy to use. So to to test this, to this live demonstration, we use an example of data that is provided in the package. This is data collected by Eric Rechstadt, that is a guy who is working with Steve Buckland very regularly. This is line transect conducted on a winter wrens in Scotland. So winter wrens is a very small passerine bird. And Eric Rechstadt collected distance data of this winter wrens on a large number of transects in a study area close to where he was working. So we can have a look to this data. The data set provided in distance is ren_lt. You can open it using the function data. When we look at the data, we have a file that is in typical form for distance sampling analysis. To make this distance sampling analysis, we need some specific information. We need the name of the study area. We need its surface, because distance sampling, it estimates densities. So if you want to get population size or an abundance, you have to provide the surface of the study area. We have here a column named sample label. Sample label is the ID of the transect. So here we have different transect, and each line, each number is the ID of a different transect. We have a column called effort, that is the length of the transect. So it's an indication of a field effort on each transect. So here we have a transect of 400 meters, about 400 meters. We have a column with an ID of the object being the birds detected in the field. And we have a column with a distance to the observer. This is the distance between the observer and the perpendicular distance between the observer and the wrens detected by Eric Rechstadt. So here, each line is an individual detected in the field with its distance. We can check at the size of the dataset using the dim function, and then we see that the dataset include 156 rows. So it suggests that we have in the dataset that Eric Rechstadt he detected 156 wrens. This is not always the case, because in distance sampling, you can have situation where you perform a transect and you detect no individuals. If you detect no individuals, you will have to add this information in the dataset. You will have to have a line with the name of your transect and no data at all in the distance, because there is no distance. It's not that zero distance, it's no distance. But you have to provide this information in the dataset, because if you do not provide this information in the dataset, then you will overestimate the density, because you remove from the dataset all the situation, all the transect where the density was 0. So this is very important to add the transect, the null transect of a null point in the dataset by providing a line with this sampling unit and no distance in the distance column. So we can check if this is the case in this dataset. And to do that, we use this function is.enna to verify that we don't have missing data in the column distance, missing data meaning that this was a transect with no observation. And we can sum that, and that in this or situation here in the RAIN dataset, we have 0 missing data, meaning that all transect that on each transect, we detected at least one individual, and we have distance for all transects. Okay, so we can now check the dataset. We can make an histogram of the distances to look at the dataset and to check if everything seems fine for distance sampling methods. So here is the histogram of the distance with a class of 10 meters. So we have all the observation. We can see that there is a strong decrease in detection between 40 meters and 100 meters. But we can also see that here we have something suggesting that maybe there are some avoidance of the observer because we have less individuals close to observer than in the class between 20 and 40 meters. So it might suggest that some individuals that were close to the observer, they move into the class, further class between 20 and 40 meters. We'll skip this information for now, and we go back a bit later on that. Okay, so we check the data, we open the file, and now we can we have to specify to distance a package what kind of measurement were used in the dataset. So we have to specify the units used for the distance, the unit used for the length of the transect, and the units used for the surface. And to do that, we use this function convert underscore units, and we specified the unit of the distance, that is meter here in the dataset, for the effort, the length of the transect, this is kilometers, and for the surface, this is hectare in this dataset. Note that depending on the version of R you have and of the package you are, they change this function. And in the new version or the older version, I don't remember, this is now a dot here. So depending on the version we have, it will be convert dot units or convert underscore units. Okay, so we specified to distance the data, the information regarding the type of the units, the metrics we have in the data, and then now we can try to fit a first model. So to fit a model, we'll use a function that is called ds, that will need some arguments, notably the dataset, and information on the key function. So we remember we have three different key functions. We have the uniform, the half normal, and the hazard rate. You can check in the help if you want to know how to name this key function. Here we choose the half normal, hn, and then we can also add some series expansion that is here specified with the argument adjustment. We provide the convert unit here. Also, you may have some trouble depending on the version you have of R. And then if you specify all these functions, then distance will fit the half normal model with no series expansion to the RAN dataset. To do that, it will use an optimization function that is by default in R and use the maximum likelihood to estimate the sigma parameters of this half normal distribution. It's very different from RMark. You don't need to have any other software like distance installed on your computer. Everything is performed in R. The maximum likelihood is performed in R, contrary to RMark for capture-recapture. Then you can fit the model and store the result in this function, in this object, but here we call ren.hn for ren half normal. We can have a quick look to a summary of the information provided by the fitting process with a summary of the object, and you have a lot of information. We have some information of the dataset. You have the AIC of the model that will be used if we want to compare different models. You have an estimate here, and this estimate is the scale coefficient. The scale coefficient being the sigma parameter of a half normal. So the sigma parameters here is 4, estimated to 4 with its standard error. And then using these sigma parameters and the width of the transect, you can get an estimate of the mean detection probability over the entire study area that is estimated here to 0.7. And using this average detection probability, you can get an estimate of the population size using the raw number of individuals divided by the detection probability. Okay, so now we can explore the result of the model, the fitting of the model. To do that, we'll use the histogram and plot the detection curve on the histogram. We'll provide some cut points for the histogram and use the function plot here with the data set and the breaks, the cut points we specified, and provide the title. If you use this line of code, you will get that. So you have the histogram with the cut points with this, of the distance recorded on the field with the cut points we define, and you will have the fitting of the model, the curve estimated by the model, the half normal distribution, the half normal curve with this shape parameter estimated to 4. So we can see here that it's not too bad, but not perfect. We have the model here estimated the detection probability is overestimated the detection probability at the distance, small distance, and probably underestimated the detection probability at the larger distance. But this is probably due to this potential avoidance of the observer by the individuals. We can have a quick look to the structure of the object using that store the result of the fitting process, the DS function. You can see there is a lot of information, and we can go in this object to look at what we want, not using the summary, but to if we want to use this information for other process, we can go directly into the object to get this information. So if you go in the object to the DDF part, you will have information regarding the modeling, the number of data, the AIC, the shape parameter, the scale coefficient, the sigma value, the average detection probability, and the abundance, estimate of abundance. So this is the most important part that you need when you will report your result, for instance, or while you will use your result to make some inference. We have some more information here, but this is largely redundant with what we just saw before. Okay, so here we just fit one model, a half normal model, and usually when we perform some distance sampling, except if we have very strong hypotheses regarding the form of the detection process, but we usually don't have very strong hypotheses on that, we fit different models. Most of the time we fit all the potential models. And so I prepare here more models, a model with a uniform function, and with a cosine series expansion, and another model, for instance, with a hazard rate and a polynomial. The strategy will go for the 9 different models to fit all the 9 different models. Then we can so we fit this model, we store the result in this object with an explicit name, and then we can use a function called AIC, where we specify all the model we fitted, and then it will organize a table with the name of the model, the number of parameters in the model, and the AIC corresponding. And you can see here that the best model in terms of AIC, the most parsimonious model, is the model with hazard rate function with a polynomial series expansion. So here the lowest IC is this model. So it means that is the most parsimonious model. And to conclude, we can go back to this notion of goodness of fit test. Of course, we can fit the 9 models on the dataset, and the 9 models they will return an estimate of detection probability and population size. It does not mean that these models are reliable. They can all be wrong. So to check that the model we use on the dataset are relevant given this data, we have to use this goodness of fit test. So there is different goodness of fit test in distance sampling, in the package distance. Some are dedicated when you use raw data without classes, and some are specific when you use classes. So here we do not specify classes when we fit the data. So the data are strictly continuous. So we have this function gof_ds that perform the goodness of fit test on the model we selected. So we have different tests. The first test is not a statistical test per se, it's a visual inspection of the fitting of the model. To interpret this is your QQ plot. This QQ plot, to interpret it, you have to check that the dot here, the point here, are well aligned with a line behind. If you have a problem of fit, you will have dot that will be very far from the line, and then it leads to suspect that you have a problem of goodness of it. We also have statistical tests, formal statistical tests, notably a test for called Kramer von Mises test that is dedicated to continuous data in distance sampling. You have to check the p-value associated to this test, and the goodness of it test is to test whether this p-value is above or below the classical threshold of 5%, 0.05. And if the statistical test is above the threshold, it means that you have no discrepancy between your data and the model fitting. So the goodness of the test is okay. If you have a p-value below the 5% threshold, it means that your model is not adequate, does not fit well your dataset. You have a strong discrepancy between your dataset and the fitting of the model fitting. So here the p-value is about 8%, so it's slightly above 5%, so it means that the model is adequately fitted to the data. Of course, it's not very far from the 5%. It's probably because, if you remember, the fact that some individuals seems to avoid the observer, and this may be explained this fit that is pretty limited. Okay, so that's all for this morning. We'll have a long break now to have lunch in France. So 2 hours break, and we'll go back at 2 o'clock for admixture model. See you. Okay. So welcome back. We are going to have a short course on N-mixture model. This is the last method we can use to estimate population size for closed population. So we'll have a short course on that with a live demo as we did for the other methods. And then I will leave you with Olivier for the part regarding the estimation of demographic parameters. So the N-mixture model, so let's go back to the traditional method to obtain an estimate of population size with row count. We go in the field, we define a study area, usually with sample units such as a circular plot or a strict transect. We count these individuals and we assume that we detect 100% of the individuals present, so that we've got an unbiased population size or abundance or density. Of course, this is false. We see that this morning a lot. There is a lot of good reason to miss some individuals in the field. So we know that these counts, when we go to the field, they are affected by detection issues. So what happens when we repeat the counts on the same sampling unit successively? So to illustrate that, here we have a pond. In this pond, we have some frogs. I think there is 10 frogs. And we go to count for these frogs. At the first visit, we count 4 frogs. So we detect 4 of the 10 frogs that are available to the detection in the ponds. Then we make a second visit the day after, or even 2 or 3 hours later, and then we count 3 individuals. And then we make a third visit, and then here we count 6 individuals. So we have variation in the counts when we conduct repeated counts at the same sampling unit with the same true abundance. Of course, you can say that this variation is due to variation in the detection probability because the condition, the weather change or the environmental condition change. But this variation can also occur even if the detection probability is the same. The detection probability, this is a random process. So when you have a random process, you can have random variation even if the mean of the process is the same. So just to have an example of that, the sex ratio in human is close to 0.5. So the probability to have a son or a daughter is 0.5. And the expected number of sons, if you have a family with four children, is 2. But of course, even if the mean sex ratio is 0.5, you have families where there are 4 sons or 0 sons. So there is random variation, not because the sex ratio changed, but because of the random process. So for the detection probability, this is exactly the same. We can have exactly the same detection probability and have random variation around the mean expected value of the detection. So when you simulate, for example, a binomial process, here for a true abundance of 5 with a detection probability of 0.5, and you conduct repeated simulation of a detection process. Most of the time, I show you here an histogram with the number of individuals detected during the count on the abscissa and the frequency of this situation. Most of the time, you will detect 2 or 3 individuals because the detection probability is 0.5 and there is 5 individuals to detect. But sometimes you will detect 4 or only 1 individuals, and sometimes you will even detect 5 individuals or 0 individuals, while the detection probability is still 0.5, only by chance. So it means that the repeated counts, it encapsulates information on the detection process and on the impedance. The N-mixture model, the rationale of a mixture model is to take advantage of this random variation to separate the random process due to the counts from the true abundance. To use these methods, we need some replication. We need, of course, some temporal replication. We need to make repeated counts on the same site to get this random process, to get this variation of detection due to the random process or the mean. But we need also spatial replication, meaning that we need several sample units to sample. There is no general rules regarding the number of sites and the number of temporal replication, but when we say several sample units, it's more 80 or 100 sample units than 5 or 10. And repeated counts, usually it's no less than 3 sessions in the field. So when you have this spatial replication, several sample units that are sampled several times with temporal replication, this is typically the same sampling design as the site occupancy models. Maybe you know these models that have been developed by McKinsey in 2002 that deals with distribution of the species, that deals with the presence of sound data. The N-mixture model emerged just after this site occupancy model. They have been developed by Andy Roy, a statistician that is working in the same team as McKenzie and Nichols, who developed the site occupancy model. So the rationale in terms of design is exactly the same, because this is a generalization from site occupancy model to abundance. To be relevant, N-mixture model to provide unbiased estimate of abundance, we need to fulfill very strong assumption. The first assumption is that the abundance at the sampling units does not change between the successive counts, meaning that between the first counts on the site and the last count on the site, the abundance don't change. This is exactly the same hypothesis of closed population that we had for capture-recapture, for instance. The second hypothesis is that the individuals have the same detection probability, meaning that there is no heterogeneity of detection between individuals. This is a very strong assumption, as we saw this morning with capture-recapture, where individual heterogeneity can arise. The third assumption is that the abundances at the sampling units follow a Poisson distribution. You can relax this assumption. We'll see that a bit later. And the last hypothesis is that the sampling sessions are independent. So here we are in the same situation as for the capture-recapture. The fact that we detect an individual or some individuals at a session don't impact must not impact the fact that you detect the individuals or the species at the subsequent session. So it means that there is no trap dependence in the detection process. So if you conduct a fieldwork using an N-mixture model design type, you will have a typical data set made of a list of sites, sampling units. The sites can be very small plots, but it can be a very large plot or even a large area. Here, each site is on a line, a row. In this example here, we have 10 sites. And then you have repeated counts on the same site that are here in a column. So for instance, on the plot 1, the first count we detected 1 individuals, then 1 individual have a count 2, and then 1 individual have a count 3. And for instance, in the plot 6, we detected 5 individuals at the first count, but only 3 at the 2 successive counts. So we have this random variation around the number of detection that vary depending on the sampling at the same site. Okay, so the N-mixture models, they can be formulated as a hierarchical model. Hierarchical models are models that try to split what we observe in 2 components. The first component, that is the state process, that describe the true state of a system. So here it's the true abundance at the different sites. So the true abundance is the n, as we used this morning, with an index to numerate the site. And this abundance has to follow a Poisson distribution, I just told you just before, with the mean abundance of lambda at a different site. And the second component of a hierarchical model is the observation process. This is the fact that when you count on the field, you not detect all the individuals present. And here, the detection process is modeled using a binomial process with the counts y at the site I and the session t is provided by a binomial distribution with two parameters, the abundance at the site I and the detection probability p. So you can write the model as this hierarchical model and use the maximum likelihood to estimate p and n, or p and lambda, from your dataset of repeated counts on a large number of sites. Of course, you can add some covariates on the abundance, on the n or on the lambda, and you can have covariates, of course, also on the detection probability. So for abundance, you can test some covariate like vegetation cover of elevation if you have some habitat selection for the species, and for detection probability, you can add the observer experience, the phenology, or the vegetation cover, for instance. I won't go too much into detail, but we will see that in the live demonstration on a true dataset. Okay, so I won't develop more the N-mixture model. Just I want to share with you the fact that this model, this method, is still highly controversial. This has been developed 20 years ago, but for over the last 20 years, this method have been very controversial and then have to be used with caution. For instance, with Thibaut Couturier, which is one of helper today, in 2013, we published a paper that show that we can have some identifiability problem when the the detection probability of a species is low or highly variable. And since this first work, several authors show that we can have strong difficulties in estimating to get reliable estimates of abundance. So we have work from Richard Barker, Emily Dennis, Link, and so on. There is a lot of work. And so this is still controversial to use this method. So we have to be very careful in using it. So I will show you during the live demonstration what kind of precaution we can use to check that the model is probably okay. But sometimes we do not know that provided values estimates are not reliable. Okay, so the N-mixture model have been largely developed over the last 20 years. They have been developed to accommodate for open population with two different formulations of open N-mixture model, the formulation of Day and Metzen and the formulation of Stuttler and Chandler. This has also have been developed to a method called generalized distance sampling. This is a method developed by Richard Chandler, and this method, it merges the concept of distance sampling and the concept of N-mixture model. Notably, it uses the N-mixture model to estimate the detection probability at the distance 0 when we suspect that this detection probability at the distance 0 is not 1. So this is a model to accommodate for temporary immigration of individuals, notably. And this model has been generalized also to simultaneously study several species, to study the abundance of several species in a community with community and mixture models. Okay, so here are the few references I cite in this very short course on N-mixture model. These papers are mainly the paper that show the limits of the method. So I encourage you to read this paper before using this method. And we can go to a short live demo on how to use n mixture model in R, and you will see that it's very easy. So let's see with a concrete example. So the dataset we will use here is a dataset collected on the ocellated lizard. The ocellated lizard is the largest lizard in Europe. It's a typical Mediterranean species that occupy Spain and the southern France. This is a threatened species that and population decreased a lot over the last 50 years. The study area is a small island on the west coast of France called Oléron's Island. And on this island, we have a relict population of ocellated lizard occupying a very small part of the island close to the beach. So to analyze this dataset, we will use two different packages, two libraries. The Unmarked library, which is a library dedicated to site occupancy modeling, including generalized distance sampling, N mixture model, open N mixture model. So this is a very useful library. And a second library, AI3 Modage, which is a library that we'll use to make model selection. Okay, so we go first to download the file and open it. It's a CSV file, so a file, just a table. You can open it with this function, read.csv2, and store it in an object that we code here dat. We can have a quick look to this dataset. So this dataset is a typical dataset of a mixture model. We have lines that correspond to sites and columns that correspond to repeated counts. So we have each line is a site. Here, a site is a plot of 1 hectare that have been surveyed 3 times during a very short interval at the same breeding reproductive season for this ocellated lizard, the same year. So we have in the first column the ID of the plot. Then we have 3 columns with the repeated counts. Counts at the first session, count at the second session, and count at the third session. So here we see that on the plot 1, we detected none ocellated lizard at the first session, 2 at the second session, and none at the third session. Then we have some covariates, two types of covariate. A covariate that some covariates that we call site covariates. It's covariates that are associated to each plot and that do not change over the field season. So we have here the column burrow. This is the numbers of rabbit burrows in the quadra in the plot. So you can see that it varies a lot depending on the plot. I will explain you a bit later why we collected this information on the sites. And we have a column with the habitats that is made of 2 different habitats, the dune and the clearance. And we have also 2 other covariates here, temperature and the month of the field session. This covariate, you can see that they have 3 different columns, and it's because this is covariate that change with the field season. We have 1 value for each field session for each plot. So here the temperature at the first field session on the first plot was 21, and it was conducted in April. The second field session, the temperature was about 25, and it was conducted in May. So this is what we call a sampling covariate because the value changed with the sampling session. We can have a look at the size of the dataset using the dimmed dat function, and then we see that we have 70 lines, 70 rows in the dataset. So we have 70 plots survey over 1 field season. Okay, we can grab the repeated counts and store them in an object that we call y here. So this is the 3 repeated counts on the 70 different plots. We can have a quick look to these counts. We can, for instance, make the sums over the columns. So to have the number of detected individuals over the 70 plots for the first session, the second session, and the fourth session. So we detected 21 individuals during the session conducted in April, 47 during the sessions conducted in May, and 44 oscillating lizards detected during the session conducted in June. So we can see that we have a strong variation of the total number of the cumulative number of individuals detected over the 3 different months we organize the field session. And we can also look at the spatial variation in detection by summing the 3 counts on the same side by summing the rows. And then you can see that there is a strong variation of the number of detected individuals between the different plots. We have plots where we have detected no individuals at all over the 3 field session, and sometimes we detected up to 8 individuals. I think there is 8 somewhere. Yeah, 8 individuals on the plot. So there is a strong variation in the cumulative number of individuals detected over the field season. Okay, so we can grab also the covariate regarding the site. So we have these 2 columns, the number of rabbit burrows and the type of habitat. We can store that in a data frame that we call here cov sites. So this is the 2 site covariates. And we can also grab the sampling covariates, the 2 sampling covariates, the temperature and the month during which the field session were conducted. So we use the 3 columns with the temperature, we store them in an object, and then the same for the month. And then we made a list. This is the format we have to build for the next steps. We made a list of these different sampling covariates. So we have a list with 2 different sampling covariates made each of 3 columns. Okay, so with this different piece of information, the row counts, the site covariates, the sampling covariates, we can prepare an object that will be used by the library Unmark to fit n mixture model on the dataset. So to do that, we use this Unmark frame pay count function that take as argument the dataset, the counts, the site covariates, and the sampling covariate, here called ops covariate. We use this function and we store its result in an object called count that is an object ready to fit model for with Unmark for n-mixture model. So the n-mixture model in Unmark is called pcount. So now we'll fit a very simple model with this function pcount, that is the function that fit n-mixture model on repeated counts in Unmark's library. So this model is made of different arguments. There is here 2 separate tilde. Each tilde is for one of the component of a hierarchical model. The first tilde is for the detection process, and the second tilde is for the abundance, the local abundance, the abundance at the scale of plot. So here we have tilde1 and tilde1, meaning that we have a detection process that is constant. We would like to estimate a constant detection probability, and tilde1, the abundance at the at the scale of the plot is also constant. We will have to have only one estimate of abundance for each plot. We provide the data set that we made just before with the function Unmark frame pay count. And we need 2 more information. There is 2 more arguments in this function. The type of model of distribution of the abundance here, so a mixture. Here we use a p value, meaning that the abundance at the scale of the plots will follow a Poisson distribution. We can use over distribution, notably a negative binomial distribution or a 0 inflated distribution. But I will tell you a bit after that it can be a bit dangerous. And we have to also to provide a value for a parameter name k. And here we fix this value to 100. So k is a very, very important parameter in Unmark and n-mixture models. This is not a parameter that will be estimated. This is a parameter that the maximum likelihood will use to check. It's a bit technical to explain, but it's a parameter that will fix the range over of abundance that the maximum likelihood will prospect to get the right estimate of detection probability and abundance. So here it means that roughly it means that we accept that we can have 100 individuals on each plot, and the maximum likelihood will search for the best value of p and lambda in a range between 0 and 100. Okay, so we fit this first model, very simple model: detection probability constant, abundance constant. We can and we store the result of this object of this function in an object called res0, and we can have a quick look to what we have in this new object after the fitting process. We have a lot of information. We have 15 slots. We have some information regarding what we ask as a model. So we have a formula, we have a k value, we have a distribution of abundance, we have information on the data, and of course we have information on the parameter estimated by the function. So we can check the result of a model using a summary applied on this object. And then we have some information in the summary. Notably, we have an information of the model we fit. And we have information on the abundance at the plot scale and detection process, detection probability at the plot scale. Individual detection probability here. So you can see, which is important, that here abundance is provided on a log scale, and detection probability is provided on a logic scale. So I won't detail more what is a logic scale. I hope you all know what is a logic scale, but it's a transformation to allow the estimation of the parameter between not on the natural scale, but it allows to estimate easily the detection probability. So the detection probability is of course not minus 0.5. It's a detection probability on the logic scale. I will show you after how we can get the true value of detection probability on the natural scale. And again, for the abundance, we have a log scale. So the abundance at the plot scale is not 0.4. It's exponential of 0.4. We also have an AIC for each model. We use Maclaurin likelihood to estimate the parameter. So we, as for capture-recapture and distance sampling, we've got an AIC of each model we will fit. Okay, if we want to have, for the very simple model, if you want to have a true value of detection probability and abundance on the natural scale, we have to back transform the values we get on the log scale and on the logic scale. And to do that, we can use a function called back transform. We specify as argument the name of the model and the type we want, and the type can be two different things. It can be the state process, so the abundance, or it can be the detection process, so the detection. Here we ask for the value of the lambda. We are interested on the abundance at the local scale, so we ask for the state process. And we've got the estimated abundance at the scale of the plot, that is here about 1.5 individuals per plot. So the mean abundance at the plot scale is 1.5 individuals of oscillated lizard at each plot. We can get a 95% confident interval of this estimate using this function here, confint, and the name of the back transform values. We can do the same for the detection process. We use the same function, back transform, the same model, and we now specify that we want the detection part of the hierarchical model. And then we have the value of the individual detection probability on the probability scale, the natural scale. So here 0.36, meaning that we detect about a third of the individual each time we go to the field to count. So it's not the cumulative detection probability over the 3 sessions, it's the detection probability for each field session. We can also get the confidence interval for this estimation. Okay, so this was just a first model, just to check the mean values of detection and abundance. But now we want to go a bit further in our analysis. So before going further to fit more complex model, for instance, we have to check that the model is reliable. The first thing to check is that when we change the value of k, the fitting, the parameter estimate, and the AIC does not change. They do not change when we change the value of k. So here I wrote 3 different models with different value of k. This is the same data set. This is the same Poisson distribution. This is the same model. I just change the parameter k that will be used by the maximum likelihood to prospect the space of parameters values, potential parameters values. So we fit this 3 model, and then we can check their AIC. And here you can see that the AIC is strictly identical, strictly equal for the 3 different value of k. It's a sign that the model is probably reliable because it is not sensitive to the value of k. So if the AIC value is stable, when I say stable, it's it's stable even at the decimal, at the second decimal, then there is probably no problem to use the model. The result should be reliable. If the AIC value decrease when you increase the value of k, and that you never reach any plateau, then it means that you have identifiability issue and the result of a model are not reliable at all. You should discard these models. In this situation, there is 2 solutions. The first solution is to try over-distribution. So here we use Poisson distribution, that is the common practice in a mixture model, but you can also test negative binomial distribution or zero-inflated distribution. It can help, but most of the time, I have to admit that most of the time, the problem is the same with the over-distribution and sometimes even worse. The other solution, when you have this identifiability issue, is to try to add some covariates on the detection priority or on the abundance to find the best model that fit to the data with the lowest AIC, or we'll do that just after. And then check again that when you change the value of k, it does not change the AIC on the best model. But unfortunately, most of the time when you have problem of identifiability, even when you add some covariates, you still have this problem on the best model, meaning that your dataset is not usable with the N-mixture model. And then you have no solution to use this model, and the results are not reliable, and you really don't have to use this result as reliable estimate. Okay, so here in the oscillated lizard dataset, we have no problem. The estimates seems reliable. The value we obtain of one individual 1.5 individual per plot is seems pretty relevant, even the data we have in the field and the experience we have in the field. So now we'll make some more models with covariates on the different parameters, the detection probability or the abundance, to improve our understanding of the population. So here we will first try to improve the modeling of the detection probability. And the first thing we tested was the effect of the month of prospection, the month of a survey on the detection probability. Why we test that? But it's very simple. We know that the reptiles, the oscillated lizard, is very sensitive to temperature. he shows a very strong phenology. It is a species that is hibernating and has a phase of activity when the weather is warm. And the oscillated and the Oléron's Island is an island pretty cold in France. It's it's the extreme north of the distribution of the species in Europe. And so we suspect that in April, it's a bit still a bit cold to detect all the individuals that may be not active at this period. So we test the effect of month on the detection probability. So we fit a model that we call res underscore month, where we added the covariate month on the detection probability. We can have a quick look to the summary of this model. We have an abundance estimate on the log scale, and we have now three estimate for the effect of for the detection probability. These three lines, they correspond to the 3 months we have prospected on the field: April, May, and June. So you can see here that we have May, we have June, but we don't have April. So I don't know if you already performed some generalized linear model in R, but here the background statistical tool is exactly the same thing as generalized linear model, and we have estimates that are formulated as we have, for instance, in this kind of model, classical statistical model. The intercept here is the detection probability of April on the logic scale. The month June estimate here is not the detection probability of the June, but it's the difference of detection between June and April. So if we want to have a detection probability for June, we have to make the sum of the intercept and the estimate of month June. And the same for May. The detection probability of May is the intercept plus the estimate of May. We also have here an AIC, and we can I shall show you here the first model with the constant model we fit first, and then the second model with the month we just fitted right now. And you can see that we gain 15 points of AIC using adding this month covariate in the detection process. So it means that the model is much better, and that we have we probably have strong variation of detection probability over the different months of the fieldwork. Okay, so now we can try to have a look to this detection probability for April, May, and June. Of course, we have these results here, but they are on the logic scale. This is not very easy to interpret. So we can use here another function that is very useful and that is common in generalizing in our model too. This is the function predict that allows to predict the values of the parameters for certain modalities of a variable. So here we create a new data set. This is a data frame for which we have only one column that we call month. This is exactly the same name that we use in the model. And in this column month, we will only specify three values: April, May, and June. This is the 3 months where we sample. And then we use this data frame in a predict, and this function predict, it has come as argument the name of the model, the type of parameter we would like to check, here the detection, as we did for instance, for the back transfer just before, the new data set on which we try to predict the values of detection, and an option happened to merge the data set and the prediction. When we print the result of this object, pred, store the result of the predict, we have these different columns. We have the predicted values of the detection probability on the probability scale, so on the scale directly interpretable for the different months and their standard error and confidence interval. So here we can see that the detection probability is 0.2, 0.23 during the month of April, and it's almost double during the month of May. So we have a much better detection probability of the individuals during May and June than during April. So that was exactly what was expected, and that was also pretty easy to detect when we made the sum. Not know if you remember, we made the sum of the columns, and in April we detected only 27 individuals, while we detected 44 individuals in May and June. So that was expected. So we have a strong variation of the individual detection probability over the month. So now we can try to complexify the model to test more interesting effect on the habitat selection, for instance, for each species. And notably, we keep the month for the detection probability because we now know that this month have a strong impact, and we add on the abundance at the plot scale the covariate burrows. Burrows is the number of rabbit burrows at the plot. And why we test this hypothesis is not just like that because we recorded it in the field. We know that the oscillated lizard population are very close to a rabbit population because they use rabbit burrows for their reproduction, but also for hibernating. So we suspect that where there is a lot of rabbit burrows, it allows to maintain great population of oscillated lizard, that when the rabbit burrows disappear from a plot, then the oscillated lizard are much less abundant because they have no more burrows for hibernating and reproduction. So we fit this model, and we can compare the AIC with the model of we fit with only the month. So we have the model with only the month and the constant abundance, and the model with the month and the number of burrows on the abundance. And we can see that we improve the model, the AIC of the model with 3 points. It's not a lot, but it's improved a bit. So this model is better, and we can now check the relationship between the number of burrows, of rabbit burrows, and the abundance at the plot scale. So to do that, we'll also do a predict, the same function as we use for the month, but now we'll use a predict on the state process, not on the det process. We'll build a new data set, a new data 2, that will be made of only one column, the number of burrow. We use exactly the same name as we use in the model. And this column of number of burrow will take the range of value we have in our dataset. So we will check the minimum value we have in our dataset and the maximum value we have in the dataset and make a sequence of these values. So we use this new model where burrows is added on the abundance, local abundance. We specify that we want the state process. We provide a new data set on which to predict, and the option happen. When we made a small plot, I'm not very good at using ggplot, but so the plot will be a bit crude. And here is the result. So in APSIS, we have a number of burrows. In the new data set, we goes from the minimum value that is 0 in our dataset to maximum value in your dataset recorded in the field that is 20, and we have the expected abundance of oscillated lizard depending on this numbers of burrow with their 95% confidence interval. So we see, as we expected, that we have a slight increase of abundance over when the number of rabbit burrows increase at the plot scale. Okay, so this is basically the end for my part on estimating abundance. Just to finish, as we did for capture-recapture, as we discussed for capture-recapture with closed test, and as we did for distance sampling with goodness of fit tests like QQplot and Kramer-Formycis test, we have some goodness of fit tests for admixture models. These tests are relatively recent. You can find them in the unmarked package. These tests, they are working using bootstrapping in the data. So how to interpret this graph? So the code is here. The code is somewhere. I don't know where. Sorry, you will have the code in the script. And when you use the code, you have this graph that is printed, and you have to check that the red line is not too far from the histogram. If the red line is on the right side or on the left side of the histogram, then it means that you have a problem of goodness of fit. And you can also check the p-value here. And the p-value is as we interpret it for the distance sampling goodness of fit test. If it's above the threshold of 5%, it's okay. If it's below the percentage, the 5% threshold, it means that you have a problem with the fit of your model given your data. So here we have no problem. You can have some more statistics here with this p-value that is the summary of the test, goodness of fit test. So here, in this example, we have no problem. A goodness of fit test, the result of the admission model seems reliable for this dataset. Just to finish, I built some more model. So here it's a list of models that I thought were interesting in terms of ecology. Of course, it will largely depend on the system you use, you study. We tested the number of burrows on the abundance, but as you can see in this model, we tested also the number of burrows on the detection process. So why we did that? We did that because we know that the observers, when they go in the field, they first look at the burrows of rabbit to check if there is or not oscillating lizard in this burrow. So the result we have just before that show that the number of oscillated lizard increase with a number of rabbit burrows could be a byproduct of a detection process. So here we fit this model to check that the number of burrows has a true impact on the abundance and not an impact on the detection process. So we test on the detection process, we turn both on the detection process and the abundance and compare the different models using the AIC. So we made a table with the different model, and here is the table, the model selection table with a mod select function that is in the AIC ModAve library. And we have a table with a different model we fitted with a AIC, number of parameters, their name, and we can see that the first model is a model where the number of burrows is both on the abundance and the detection probability. But you can see that these two first models have very, very close AIC value. There are very, very small difference, meaning that the number of burrows on the detection probability has probably a very low impact, or we are not sure that there is an impact. But the number of burrows on the abundance here has a true impact because the model without this burrow on the impact is much higher in terms of AIC. Okay, so this is the end for the part of estimating abundance, population size, or densities in a closed population. So this is the end for me for this workshop also. I hope it was okay for you. You will have the course on the courses in the website. You also have the script with all the codes and the sample and the dataset on the website, so we can go back to this course and this script later tranquilly, calmly. And now I leave Olivier to talk. We have 10 minutes break, and for the rest of the day, we'll deal with Olivier with demographic parameter estimation. Thanks a lot.
Okay, that's my turn now. I'm Olivier Jimenez. Can you hear me, or can you make a sign to say? Yeah, okay, perfect. Okay, before I start, I just wanted to maybe go back to the website and show you where everything is, the material, and all you need to follow the live demo in particular. So you have this website, we've sent you the link, and on the website, okay, there's description of the workshop and blah, blah, the schedule, but the most important parts are on top of the website here, where you have this pull down menu with the lectures, okay? You have also a PDF with all the slides that we will probably update after the workshop, because we're finding typos, and also we've updated the slides from last year. So we'll update that probably early next week. And also you have the live demos here. So if you click on it, you're led to slides with the live demo. There is this menu here for the data sets. So if you click on it, it will download for you a zip file with all the data sets. Okay. There is something about software installation for those of you who are working with a Mac, because it's a bit tricky to install a RMark that we're going to use in particular in that lecture on estimating demographic parameters. And also the cool thing, or I think, is that from last year, we've gathered all the questions and answers we gave last year to the questions of the attendees in a PDF file. So it's available to you. You can just have a look if you want. Maybe you'll find some questions you have this year, and we'll try to do exactly the same thing this year. I mean, gathering all your questions and our answers, and maybe I don't know, maybe improve our answers if we feel that we need to improve them, and gather that in a PDF file and share it on the website. And last thing I wanted to show you is this icon here. This will lead you to GitHub, which is kind of a repository where we put everything, all the material that we use to give the lectures, live demos, and also build the website. So if you click on it, you'll go to you'll be sent to GitHub. So this is a bit ugly, but mainly what you need to remember is this. All the slides, the website, everything has been written in R using this R Markdown package. For those of you who know about it, if you don't know about it, that's fine. It's just that in this directory here, slides, you'll find all the slides for the lecture. Okay, so this is this kind of file, for example, conclusions, the slides for the conclusion of the workshop. You open it and you will see that there is some R code somewhere. Or maybe I will open something else. Abundance. So that was Aurélien's lectures, and you have all the R code that is available from here. Okay. Same thing for the live demos. So this is this thing called tutorials. If you click on it, you will get everything here. So you just have to explore those directories and you'll find what you need. And maybe it's, I think, yeah, there's something simpler. If you want just the R scripts, if you go in the pull down menu on live demos, you have this option here with all R scripts together. So if you click on it, you have you download this R script with everything in there. So if you open it with a text file or R or RStudio, whatever you like, you have everything, okay? For the live demos, right? Okay. So I hope it's clear now. Okay. And back to the lecture. Okay. So my lecture is about, let me just resize everything. Okay. Okay. It's about estimating demographic parameters. So we've seen with Aurélien oops, that's the live demo, sorry. Yeah. So we've seen how to estimate the outputs of the dynamic of a population. In that, we've seen how to estimate population size using distance sampling and mixtures, capture-recapture models. And in this lecture, we thought that would be great to open the black box of the population dynamics and see how to estimate demographic parameters, namely survival and probably dispersal at the end of the lecture. Okay. So now, Plate, what we have is three main lectures: estimating survival with capture-recapture models, including discrete and continuous covariates to try and explain variation in survival, and estimating transition between sites and or states, which will help us to estimate dispersal. Okay. So the last one, we will see that tomorrow morning. Okay, let's get to it. Estimating survival with capture-recapture models. Okay, first things first, how do we mark animals to capture, mark, and recapture them? So we may use artificial marks like rings on legs here on this bird, or GPS collars like on this ungulate here, or you may use natural marks like on this carnivore here, natural marks here on the fur, or indirect signs like scats, feces, on some bears here. Well, anything that can help you to identify individually an animal. Okay, and from there you can go to capture-recapture data, as we've seen with Aurélien. Like, let's say we have 3 capture occasions, so you go on the field 3 times, days, weeks, years, whatever, and you have 2 time intervals defined by the capture occasion. So the first time interval and then the second time interval. Okay, 3 capture occasions, and in rows, these are the individuals, right? Ones are for detections and zeros are for non-detections. The difference with what we've seen with Aurélien is now the population isn't closed any longer; it's open. So individuals may die or appear in the population over the study period. In terms of parameters, let's say we have 3 capture occasions, like I said, T1, T2, and T3. We will need 2 types of parameters: survival, the fact that you survive from one occasion to the next one, and detection probabilities that we've seen with Aurélien, the detection probabilities being denoted P. P2 is for the probability of recapture at time 2, and P3 is for the probability of recapture at time 3. Okay, we condition on the first occasion, meaning that basically the probability of first capture is 1. Okay, you need to be captured to enter the data set. Okay, let's go for a formal definition of the parameters. Phi I is going to be the probability that a marked animal in the population at sampling occasion I survives until the next occasion, so I plus 1. So it was a T in the previous slide, so I or T, whatever, it's the occasion, okay? And remains in the population. The idea is that the individual doesn't permanently emigrate, okay? So survival is, in that case, is true survival. If you have some emigration, then it's what we call apparent immigration. Okay? And parameter Pi is the probability that a marked animal in the population is detected, captured, or observed at sample occasion I. Okay. So one important thing to keep in mind is that detection operates at a sampling occasion. It's the probability of being recaptured, detected at time T, second occasion, third occasion. Okay, it happens at a punctual event being detected at a time occasion, at a sampling occasion, whereas survival operates between 2 time occasions over a time interval. Okay, that's something you survive from one time occasion until the next one. Okay, so this is a a distinction between these two parameters, detection and survival, that you will need to keep in mind, in particular when we get to incorporate covariates. Okay. How to estimate these parameters from the data we have? Okay, so we'll use the data like we've seen with Aurélien. Let's go back to our example, 3 time occasions. Let's go through a fake example, a simple example. Your first captures marked and released in the field, okay? And then you may be you may be alive and present, or or I will just mask. Yeah, okay, better this way. Or dead or emigrated, okay, between the two time occasions. And then at the second time occasion, you either detected or undetected if you're alive and present, and if you're dead or if you die or emigrate over the time interval, well, you're done, okay. And then to kind of write probabilities in a probabilistic way. I got it. The fate of this individual, we will use the survival between time 1 and time 2, and then the probability of being detected at time 2, so P2. Or if you're non-detected, 1 minus P2, okay, the complementary probability. And if you die or emigrate, then it's just 1 minus phi 1, okay, the complementary probability of the survival probability. Okay? And if there is no immigration, it's true survival, so it's just alive or dead, right? And then same thing for the next time occasion, T3. You may, if you were detected, you may remain alive and present, or die or immigrate. If you were undetected, then you may remain alive or die, and then with some detection probability and survival probability. Okay. So that's a way to kind of describe the fate of an individual over time and all possibilities that can lead to some encounter histories. How do you describe the fact that you've been detected or not over time? And each sequence of hours leads to a different capture histories. Okay, if you were alive at each time occasion over each time interval and detected each time, then it's a 1, 1, 1. Okay, you've been detected at all capture occasions, or you may be missed at the last one. And interestingly, the 1, 1, 0, you detected, and then missed on the third time occasion, may be the results of two true kind of a capture history. At the last time occasion, you may be alive but went undetected, or you just died and of course you couldn't be detected. Okay, so it's two different fates that lead to the same encounter history, right? So you need to account for these two different fates when you're going to write the probability of this data 1, 1, 0, right? And it's even worse for the probability 1, 0, 0. There are three possibilities, 3 different true fates that could have led to this 1, 0, 0 detection probability or encounter history, right? So how to write that in a formal way? So I will show you that in a slide, and then you can forget about it, but it's good to have seen it at least once. Maybe some of you will understand better the probabilities this way. Maybe you understand better, right, if it's written that way. I mean, it's a matter of perception. Okay, so let's say we go through this fate. Captured, alive, then detected, then alive again, and then detected. So how to write the probability of this encounter history? 1, 1, 1. Well, you were alive on the first time interval with a probability phi 1. Then you were detected you were recaptured at occasion 2, and then you were alive again because there is a 1 the last time occasion with probability phi 2, and then you were detected at the third capture occasion. So it's the probability of being recaptured at time occasion 3, so P3, okay? So that's the probability of this capture history or encounter history 1, 1, 1. Now, what about this encounter history 110? Like I said in the previous slide, there are two possibilities for the last detection, non-detection. Either you went undetected, or it's just that you died on the last time interval. Okay, so you have to account for these two mutually exclusive events. So either you were alive, so phi1 p2 for 1 okay, so it's you survived over the first time interval, so it's the same thing for the two possibilities, and you were detected on the second time occasion, so it's phi1 p2, and then you were also alive on the second time interval, but you went undetected, so it's phi2 1 minus p3, right? Or you were alive on the first time interval and detected on the second time occasion, so phi1 p2, like for the first option, but you just died on the second last time interval, so 1 minus phi2. Okay, so it's the two possible alternatives, and they are mutually exclusive, so it's the sum of the two probabilities. Okay, and then you can rearrange those terms by factoring out phi1 p2, and you get this form for the probability of 110. Okay. So this is for one individual, one encounter history. Imagine you have to do that for all your individuals, all your animals, and it's going to be cumbersome, to say the least. So the good thing is that there are some packages that do the work for you. But let's say we have 4 different encounter histories. So we wrote the probabilities for you, and then from there, you can write the likelihood, which is the probability of the data given some model taken as a function of the parameters of this model. And the idea is to maximize this likelihood if you are in a frequentist approach. We won't go through the Bayesian approach, but basically in the Bayesian approach, you also need the likelihood. That's kind of the core of the two approaches, either the frequentist or the Bayesian approach. So the likelihood is the probability of the data, and the data here, just ignore these ones. The data is just the 111, the encounter histories. So it's just the probability of the encounter histories 111 raised to the power of the number of individuals who have this particular encounter history times the probability of the other encounter histories raised to the power the number of individuals with that particular encounter histories. Okay, and that way you write down the likelihood of the capture-recapture model you're interested in. Okay. In that case, when you have a time-varying survival probabilities and time-varying recapture probabilities, detection probabilities, this is what we call the Cormack-Joly-Silber model, and I'll get back to it in a minute. Okay, so we have our likelihood, and we want to maximize the likelihood function, which means we want to find the values of the parameters that give us the highest value for the likelihood. Okay, so the parameters are the two survival probabilities and the two recapture probabilities. So we're going to inspect visually the likelihood function. So it's a function of those parameters. And to make it simple, we're going to assume that those parameters are constant over time, which means that we have only one survival parameter and one detection probability. Okay, so phi1 is phi2 is phi, and p2 is equal to p3 is equal to, let's say, p. And if you do that, let's say we have survival on the y-axis and detection on the x-axis, then you have this nice surface where the more when it gets yellow, it's you are at the top of the mountain, and when the greener it is, the more at the bottom of the mountain you are, at the surface of the likelihood you have. Okay, so I've simulated some data, and the true value, the highest value for the likelihood is here. And when we apply the maximum likelihood estimate, trying to maximize the function using some numerical algorithm with R, with the package that we will see, RMark, then you get this value, which is very close to the true value. Okay, so it's doing the job we are asking it to do. Okay, we're finding the maximum of the likelihood, which is the maximum, which give us the maximum likelihood estimate. So it will give us detection is around 0.6 and survival is around 0.7. Okay, so that's these two values give you the highest value for the likelihood. So these are the maximum likelihood estimate of survival and detection probabilities, right? Okay. So that's the general principle of maximum likelihood. That's the maximum likelihood theory, actually. Yeah? In that case, we have two parameters, but it's going we're going to use exactly the same theory to fit models with more parameters. And that's actually the theory that Aurélien used to get estimates for distance sampling models, n-mixture models, and also capture-recapture models for closed populations, right? Okay, a bit of history. It's a parenthesis that I like to make because it gives you some context about how these models were developed and when they were developed, because actually, well, for some of you, these models might appear very old. They were developed in the 60s, but actually, the 60s are not that far. It's not that old. I wasn't born in the 60s, but it's not old anyway. So history of the Cormack-Jolly-Sieber model. It's a nice paper by Steve Buckland that Aurélien cited in his. Thank you for the. In his lecture, Steve, who developed distance sampling models and many other, he made so many contributions to statistical ecology that would take a day to talk about it. Anyway, so he wrote this paper, a conversation with Richard Cormack, which is one of the three people who came up with this Cormack-Jolly-Sieber model in parallel. And it's a nice story because actually two of these authors, George Jolly and Cormack, Richard Cormack, were actually working in the same building. And they were playing some game like play Quick Spin. I don't know if you know about this game. It looks like a chess game anyway. So they were interacting with each other. They were playing some games together, but they would never talk about work. And they were working with on this very specific model in parallel without knowing about the other one, the other research. So that was really funny. And they actually published a paper the same year, or 1 year of gap between the two. And Cormack was saying, well, you have to imagine that actually we were not really we were just friends, and but we wouldn't talk about work. So there was no way that we would be aware of what the other one was working on. And then I think Sieber moved to I don't know. Oh yeah, there was also a Sieber who was involved. So it's the third author, and while they were exchanging mails, because at that time emails were not did not exist, so it would take time anyway. So that's a very nice if you have some I don't know, some time to read it. A conversation with Richard Cormack, which appeared in Statistical Science. It's very nice. From an epistemological point of view, it's very nice to see how research was done for 60 years ago. And there's this other paper, this 1992 paper in Ecological Monograph by actually the lead author, Jean-Dominique Breton, is in our team. He's retired now, but is still very active. Modeling survival and testing biological hypotheses using marked animals. It's kind of it's a landmark paper with several case studies, actually 4 or 5, and introduces. I think that's the first paper that introduces the use of AIC in ecology, and it's a very nice paper, a long paper, like 60 pages. 60 pages roughly. But it's very well worth a read if you have just take the time to read it. It's very, very interesting. Okay, let's practice. We will use this famous deeper example, white-throated deeper, Cinclus. It's famous from this paper actually, because The data, I think the deeper data was one of the first data set that was shared to the community. Now we're talking a lot about open science, reproducibility, sharing data, sharing code, and blah blah. But you have to imagine that 10 years or 20 years ago, or even yeah, it wasn't the habit to share data, share codes. And this guy, Gilbert Marzolin, who is still doing the field work, he initiated this program back in the 70s, I think. And he's still doing the field work, capturing deepers on the rivers with nets. And he was one of the first ecologists to share his data. And actually, this data set was used repeatedly, in particular to illustrate new methods, new capture-recapture models. And so it was very, very influential in that sense, and sharing data to help others to illustrate new models, new ideas. And okay. So we will use this data set. So it's 294 individuals captured and recaptured between 1981, last century, and 1987, okay, with non-sex and wing length. So I'm going to try, yeah. So you have individuals in rows, you see, the 299 individuals, and you have ones for captured that specific year and zeros for non-captured. And you also have two covariates, individual covariates, sex, male or female, and wing length. Okay, so it's 95 millimeters. Yeah. And for each individual. Oops. Okay. Right. Okay. So with that, we're going to try and estimate survival. Okay? So how to do that? That's the first live demo, I think. Yeah. I just want. It doesn't work. I like my animation. It doesn't work. Okay. Okay. First live demo. A simple, well, a Cormac Jolly-Sieber model, let's say. What time is it? 3:30. So maybe I have time to go through the code. Let me try that. So I will go back. Yeah, well, I will go through the slides. Okay. So first thing first, we're going to load to read the data file. Okay. So it's a CSV file, which is called deeper.csv. So to get the data, you go back to the website, and it's here in dataset. Okay. So if I download it, I go to the zip file, click, I unzip it, and you have several data sets, including the ones you used this morning with Aurélien, and those three data sets that we will use together, AllGIS, Deeper, and GIS. If you have a look to the deeper.csv, it's exactly what I showed in the slide. Individuals in rows, 294, years in columns, ones and zeros, and this sex column and wing length column, okay, that we will use in a minute. Okay. Now we're done. So we read this data set. So I use this function, read_CSV, which is a readr. It's a function from the readr package, which is within the tidyverse series of packages. Okay, you can use, well, whatever package you like to, or function you like to read a CSV file, that's fine. And if I display this file just by typing the name of the file, which is, I've stored everything in this very original name, deeper_CSV, okay? And now I display this data set. So you see it's a table data frame, roughly. In columns, time, the individuals in rows, and we display here the 10 first rows. And then you have more rows, 284. Okay, so it's 294 in total. And you see the ones and zeros, you see this column sex, and there is an extra column wing length that is not displayed here, just to pack things in on the screen. Okay. Okay, the reading is fine. So now we're going to do some formatting, because to use RMAC, the package that helps that you used this morning and that we will use to estimate survival, we need the data to be in some specific formats, specifically this format. We need to have a data frame with is it a data frame? A data frame with 3 columns. Well, at least with a column with the capture history. CH is for capture histories. It's a single column, and each component of this column, each cell of this column, it's a character with the ones and zeros denoting detections and non-detections. Okay, so it's not a column per time occasion. Now everything is pulled together in a single column, a character column. Okay, and the format is a character. And here you have, for this first individual, you have the 7 time occasions, and it was detected, and just missed the last year, 87. And then you have 2 extra columns for sex and wing length. Okay, so it's a data frame with 3 columns. The first one is just the capture history for each individual, a character file, a character column. And then sex is a character column also for males and females, and wing length is a numerical column. Okay, so that's the previous slide. That's how I do that. There is this very, very convenient function in the dprior package, I think, Unite, which will pull together the several columns in a single column. Okay, so here what I do is that I take the file, the object I've just created, deeper_CSV. I select all the columns, including the detections and non-detections, so from 81 to 87, and I unite them in a single column with format character, and with nothing, no space, no comma, no nothing to separate them. Okay, so it's just there is nothing here between the two. How do you call that? It's guillemets in French, but I can't remember the okay, maybe someone can help me in the chat. How do you call these two guillemets? Oh. Double quotes. Oh, quotes, yeah. Yeah, of course. Thank you. Okay, and then my 2 extra columns for sex and wing length. Little detail, like you would do in standard linear regression or multiple regression or whatever in R. With continuous covariates, we tend to scale them. So you subtract the mean and you divide by the standard deviation. And there is a function in R called scale that does both operations for you, subtract the mean and divide by the standard deviation of the covariates you want to standardize. Okay, so it's this function scale, which is very convenient. Okay, I put everything in the data frame and I get that. Okay, so we're almost done. The formatting, we've read the data set, we've formatted the data, and now we're ready to use RMAC to estimate survival. So there is a let's go straight to RMAC, and there is this function mark that does by default it fits a model with constant parameter. So if you just apply mark to your deeper data, which is the data frame we've just created, okay, it will fit a model for you, a model with constant parameters. Okay, so it's a way to use a mark like in a second. It's not very useful, but still it will show you whether everything is fine and the data is fine, and whether mark is throwing you some error messages or warning messages or whatever. Here it works perfectly. So we fitted the model with phi constant. So it's really like in R, 1 is for intercept, for constant parameter, and P1, it's for an intercept, so constant parameter. There is no covariance, no time effect, no edge effect, no nothing. Okay. So it's 2 parameters, phi, survival, and P for detection probability. 2 parameters. we get the deviance here, which is -2 times the logarithm of the likelihood, okay, evaluated at the estimates of survival and detection, and AIC corrected for some small sample size AICC. Okay, it's a correction for small sample size. In our case, the sample size is quite okay. So AIC and AICC should give the same value. Okay, and you get estimates here, 0.24 for survival and 2.23, weird, for detection. So it's probability, it should be between 0 and 1, and we get something that is much higher than 1. We'll see why in a minute. And you get standard errors, okay? And you get the lower bound of the confidence interval. By default, it's 95%, okay? And the upper bound of the confidence interval for survival and for detection, okay? So why do we get crazy value for detection probability? It's just that the estimates we get are not on the scale 0-1. They are obtained on the logit scale. So I will get back to that in a minute. It's not on the scale you really want to work with, but it's very convenient. So I will show you how to go back to an estimate that makes sense. Okay. Okay. Let's have a look to what we get. So when we call mark, we put everything in this object, phi.p. You could call it whatever you want. I like. It's nice to have a object name that make. That are kind of self-explanatory. Okay. So here it's phi.p. So I fitted the model with two parameters, phi and p, and constant effect on constant parameters. There is no t or covariate or whatever. Let's have a look to what's inside this object. So I will use this function str, which gives us the structure of an R object. And here you see that by typing that structure of phi.p, it's a list of 25 elements. Okay, so it's a long list. Let's have a look to what we have. Names of phi.p. You see that we have 25 elements in this list, and we have many things: the data, model, title, model, and parameters. Nice. Covariates. Well, in our case, we don't have anything. Model parameters. Gets interesting. Results. So let's have a look. So we're going to use this element, results, and if you have a look in that, there are other elements in that element. In particular, we get the real estimates, the parameter estimates. Real in the sense that they are in the 0-1 scale, which is the scale we want for probabilities. Okay, so this is really what you are after. Phi.p $ to access the results, and then $ again to access the real element of the results element from the phi.p object. There is an easier way to do it. I will show you that in a minute, but let's have a look for a second on that. So you get survival is 0.56, which is well, it makes more sense than well, the other one was 0.24, so that was okay. But you remember the detection was 2.23. Here it was a knowledge scale. So here it's 0.90, which makes much more sense for a parameter that a probability that should be between 0 and 1. Okay, so detection is very high, and survival is a kind of a 60%, which for a passer-in like deeper makes well, it's kind of realistic. It makes sense. Okay, and you get the standard errors and also confidence intervals for survival and confidence interval for detection probability, right? So these are the real parameters. Some variation around that one. So you remember that I just typed in mark. So that's the R function I'm using from the RMark library package. And then I just apply this function to the deeper data frame I've created a few slides back. Yeah, okay. That contains the detection, non-detection, sex, colon, and wing length colon. Okay. So far we haven't used the covariates, but hang on a minute. Okay. Now I'd like to do something a bit more interesting. I'm going to process the data in a way that I will tell R and RMark, okay, there is a group effect, there is a group covariate, sorry, namely sex, okay, for males and females. And so to do that, I'm going to use this function process data, which will which will prepare everything, the number of capture occasions, time intervals, and above all, groups, so that when I'm getting to fit models with a sex effect, for example, everything is set up, okay? So this is a first step. You process the data, and then you create this design matrix that you've seen with Aurélien. It's kind of it's creating the most general model that you can think of. So a model with a time effect and group effect. Okay, so it's kind of an umbrella model, the most complex model, and then from that model you will fit simpler models from that very complex model. Okay, so it's just a way to prepare things, to set up to prepare everything and to be ready to fit the models you want. Okay, so you make the design matrix using the data you've processed, and then you define the structure for survival and detection probabilities that you will want to fit. So I want to fit a few several variations of the constant model, the model with constant survival and detection probabilities. I'm going to fit a model with a time varying survival. So here survival won't be constant whatever the time interval, but survival will depend on the time interval. So we will have time variation, which may be caused by, I don't know, environmental pressure on dippers or environmental conditions. Okay, and same thing for detection. Detection is going to be either constant or time varying, and we will consider all the possible combinations. So a model with a time dependent survival and constant detection, time varying survival and time varying detection, and so on. Okay, so in total we will have 4 different models with the 4 different combinations, right? Okay. For example, let's fit the original Cormack-Joly-Sieber model to the deeper data, which is a model where both detection and survival probabilities are varying across time. Okay, so we use again this mark function from the RMark package, but now instead of just feeding this function with the deeper data frame, deeper.csv data frame or underscore the CSV data frame, we will use the 3 objects we've created, the processed data, with the sex effect, the sex group, the sex covariate, and the design matrix. And also, last thing, the model parameters I want to fit. So by default, when you don't specify anything, it's a model with constant parameters. Now I'd like to fit a model with time varying parameters, time varying survival and detection. So to do that, I just create a list where I say, okay, survival is going to be phi t, and phi t is actually it's another list where I say the formula, so it's really like in a GLM or LM formula, is equal to tilde and time to say it's a time effect, right? Okay. I think I forgot to record everything now. Oh no, it's recording. Great. Okay. Oof. Okay, let's fit this model. So you just type in that and you get this. So it's a summary of what you've used, a model with time effect on both survival and detection. It has 12 parameters. 12 parameters because you have 7 capture occasions. So survival is working on time intervals. If you have 7 time occasions, it's 6 time intervals. Okay, so it's 6 survival probabilities. And regarding detection probabilities, remember we capture probabilities that we're estimating. Okay, the detection at first sampling occasion is kind of a, because we condition on the first occasion, it's basically 1. Okay, so it's at the end of the day, if you have 7 capture occasions, you estimate 6 recapture probabilities. So it's 6 plus 6, it's 12 parameters. Okay, and here we get some estimates. You know, you get negative estimates, which for probability is a bit weird. Again, these estimates are on the log scale. We don't want really to spend too much time on that. We want to extract the real parameter estimates. So just extract real. And then what you get is survival on the first time interval is 72%, 43%, 48%, and then increases back to 63, 60, okay, and 77. You see that there is something happening here on these 2 time intervals between occasion 2 and 3 and 3 and 4. And we will see that actually the population of deeper that we're studying in this case study here suffered from a flood, and survival greatly decreased over these 2 time intervals. And we'll see in a minute how to actually test that formally, statistically. Is there a flood effect on survival? Okay. And for detection, you see the recapture probability at occasion 2 is 70%, and then at third occasion it's 90, 91, and so on. Okay. Okay, now let's fit a model with a time varying survival and constant detection probability. So you just have to amend the list here with the parameters, and you fit that again. You see that it's only 7 parameters, 6 survival probabilities, and 1 detection probability. Same thing for constant survival and time varying detection probability. Again, 7 parameters, 1 survival probability, and 6 recapture probabilities. And you can, so we have 4 models, a model with 4 models, and you'd like to be able to compare to assess the relative fit of these models to one another. To do that, we use AIC, and we use this very convenient function collect models. So you fit your 4 models, and at the end of this process, you just say, okay, collect all the models with the function collect.models. And RMark is doing the job for you. It's a very so RMark was written by Jeff Lack, which is who is working at the he's retired now, but he used to work at the NOAA in the US, and he developed this RMark package. So it's calling this software called Mark, which was developed by Gary Wright, another colleague from the US, and Jeff developed this kind of R package to call Mark from R. Okay, so it's a very convenient package. Anyway, so it has the RMark has this package, this function, sorry, called collect models. It gathers all the models together and computes the number of parameters, extracts the number of parameters, the AIC value, and ranks those models from the model with the lowest AIC value to the highest AIC value. And you see that in that case, the model with constant parameters seems to be the model best supported by the data with this AIC, which is the lowest. Okay. So the best model has constant parameters. Oh, perfect. I think that's the next. Yeah. Okay. So I think it's 10 to 4. So it's time for a break. Let's go for a 10 minutes break, and we'll resume we'll resume the lecture with how to incorporate covariates to assess, to explain explain variation in these parameters that we're interested in, namely survival and detection probabilities. Okay, so see you in 10 minutes. Okay, let's get back to it. So the last lecture of the day and live demo of the day is going to be about how to integrate, accommodate, or include discrete and continuous covariates in these convex Seaborn models or open population capture-recapture models to estimate survival and detection while accounting for imperfect detection. Okay, so that's what we're going to focus on for the next 50 minutes. Okay, including 2 or 3 live demos. Okay, first question is, can we explain individual heterogeneity or variability in a particular survival? And that's something we are very much interested in. Is there some variation in some individual covariates, like in particular sex or wing length in our case, that could explain the fact that some individuals survive better than others or less well than others? Okay. So we're going to start with a discrete covariate to make it simple. Well, it's not necessarily simple. It's just it's maybe to fix ideas. It's a bit simpler to start with a sex, because it's just 2 values, males or females. You're a male or female for the birds, and we will continue with continuous covariates with mass, or in our case wing length or size, whatever. Okay, so for deeper, just as a reminder, we have sex, male and female for each bird, and also wing length that was measured at capture. Okay, first capture. At first capture, we have wing length, which is, for example, 95 millimeters or 88 millimeters for that particular bird or that one. Okay, let's start with incorporating a sex effect on survival, I think. Yeah. So we're going to use 0 for female and 1 for male, okay? The first thing we're going to do is to write the relationship between survival and sex. So for survival individual A, well, that's the end of the day, I'm a bit tired. Anyway, so for individual I, the survival is going to be a function of 2 parameters, an intercept and a slope, times the covariate that gives you the sex of the individual I. Okay, so 0 if it's a female and 1 if it's a male. Okay, so we're going to use this function logit. I think you've seen it with Aurélien, but I will spend 1 or 2 slides on it just to try to make it even clearer. What is this logit thing? Okay, what's the justification to use this logit, what we call a link function, like in GLM, generalized linear model terminology? So when you use covariates, you could be tempted to write just directly that survival for individual I is equal to beta 1, an intercept, plus a slope beta 2 times the value of the covariate. Okay, that's what you would do in a linear regression, for example. Okay, the thing is that this parameter, the survival here, is a bit special. It's a probability, so it lives between 0 and 1. Okay, it doesn't live between minus infinity and plus infinity, and it may cause some problems, because when you get to the estimation of these parameters, and when you use the maximum likelihood theory, the risk is that some values of the betas that you're trying to reach the maximum value of the likelihood make survival for individual I negative or higher than 1, which is not acceptable for a probability. Okay, it's between 0 and 1. So how to kind of force survival to remain between 0 and 1, and to be able to explore values for beta 1 for intercept and slope, so that we reach the maximum of the likelihood. So to do that, the idea, which is borrowed from the generalized linear modeling framework, which was formalized in the 70s, okay, 73, the book on GLMs. The idea is to estimate parameters on what I've called, I don't know if it's a correct term, but I think it conveys the idea. It's a safe scale, in the sense that whatever the values for beta 1 and beta 2, the survival will remain between 0 and 1. Okay, so the idea is to try to estimate beta 1 and beta 2 between minus infinity, for survival that varies between minus infinity and plus infinity, and then to go back to the original scale 0, 1. So we will use this function logit. Okay, we will transform survival. So y here is going to be survival by using this logit function, which is the log of the object you're interested in, survival, let's say y, over 1 minus y. Okay, and this quantity here lives between minus infinity and plus infinity. And this is on this scale, which is between minus infinity and plus infinity. I'm sorry, I'm repeating things, but it's just just for you to maybe better understand. This is on this scale that we're going to write that survival is a function, a linear function of the sex effect, right? And then we're going to go back to the original survival between 0 and 1 by using what we call the reciprocal logit function, which is logit minus 1, raised to minus 1. But anyway, this is this function. You don't have to remember the form of the function. It's just that you need to remember that actually we get estimates on the logit scale, and then we need to go back to the original scale by using this back transformation with the reciprocal logit function. Okay. So again, the software, the package will do that for you, but it's cool that you keep that in mind, that the estimates you get are not, that's what we've seen previously in the first live demo. You get estimates that are given on the logit scale, okay? So it's not directly what you're interested in. You need to do the back transformation and get the real estimates like we did before. Okay, graphically, what does it do? What does it mean? The logit function works this way. So you have this logit information, and the logit of survival, so logit of phi, lives between minus infinity, let's say minus 10, and plus 10, okay? So in that way, whatever the values of beta, the logit of survival, it's okay. It can be negative or higher than 1, no problem, okay? And survival is between 0 and 1. And then you apply the back transformation using this reciprocal function, and now you get the survival probability between 0 and 1, okay? After back transformation. Okay, let's go back to the sex effect. Let's use, like I said before, sex that takes value 0 if it's if the deeper is a female, and 1 if this is a male. And we write logit of phi, so the survival of individual I, is the linear function of sex for bird I. Okay, beta 1 is the intercept, and beta 2 is the slope. So now, if it's a female, we say that sex is 0. So this relationship is simply logit of phi is beta 1, okay? Sex is equal to 0, so beta 2 times 0 is 0. So we're just left with logit phi 1 is beta 1, okay? And then if it's a male, sex is equal to 1, so it's beta 1 plus beta 2 times 1, beta 2, okay? So logit of the survival of bird I, which is a male, is beta 1 plus beta 2, okay? Right, so beta 2 is just the difference between male and female survival on the logit scale. That's the thing you need to remember, okay? So Mark and R Mark will give you these estimates of the betas of the intercept and slope on the logit scale, but it's not directly what you're interested in, okay? What you want is phi 1, you're not really interested in beta 1, but Mark is working with the betas. That's the thing that is a bit annoying. But it's what we need to make sure that survival will be between 0 and 1. So then you need to apply the back transformation to get survival on the right scale between 0 and 1. Okay, so you need to back transform beta 1 and beta 1 plus beta 2 to get the female survival and the male survival. Right? Does it make sense? So it's very much like what you do with an analysis of variance with one factor here. It's a sex effect with 2 levels, male or female, right? Okay. And then you can imagine you have several factors. You may mix with a continuous covariate, and then you get some analysis of covariance, whatever. It's just that when we have this logit link, And this is what we use in generalized linear models as well, logic link or log link for Poisson regression, whatever. Okay. I go for link. I go for wing length effect. Okay. So what about, so we're done with the sex effect, and we'll go through a live demo to see how it works in practice. But let's proceed with a wing length now. So it's a continuous covariant, okay? It's not just a discrete values like ones and zeros, males and females. But now it's a continuous scale. So wing length may vary between 40 millimeters up to 100 millimeters. So it's continuous on that scale. And we'd like to include this covariant to try and explain survival as a function of wing length, okay? Well, we're going to do exactly the same thing, but now we don't have a discrete value for the covariant. It's just a continuous value, but it's very much like what we did for sex effect. And we have an intercept and a slope, and it's the same thing as before. We use the logic link to make sure that survival is between 0 and 1. Okay, let's do that. Now let's do that on a live demo. Okay, let's go back to something that makes probably more sense. Okay. So first thing first, you remember we do, what do? We process the data, okay, with the sex group. That's what we did in the previous live demo. And then we create the design matrix with the time effect and group effects, okay? So these two steps are already done. And now we define some effects on the parameters. Okay. So because we've read in the file saying that there is a sex group, that's the column with males and females characters, we can directly use the sex keyword, okay? It's the name of the column. So we say, okay, let's define a phi sex effect. You could call it whatever you want, but in that case, I'm using phi sex. It's a list with the formula that is going to tell R mark. Okay, it's a sex effect. So with this male-female value for each individual. And then we proceed the same way as before. We go back to our mark function. We feed it with what? With the process data, the design matrix. And then for the model parameters, we say, okay, let's start with a model where survival is sex dependent, is a function of sex. A linear survival is a linear function of sex. And so there are two survival parameters, one for females and one for males, okay? And constant detection probability. We feed that in RMark, and we get okay, a summary of what we've done, okay? Sex effect and survival, and detection is constant. Remember, 1 is for intercept, like you would do in a GLM or LM. 3 parameters, 2 survival probabilities, 1 for male, 1 for female, and 1 detection probability. So it's 3 parameters. You get the deviance, the AIC, and you get those parameters here. And now they should make a bit more sense than before. We get the estimates of the betas, okay? So these are the estimates on the logic scale. So you get the intercept of the survivor. So it's beta 1 in the lecture. I think it's still here for the sex effect. Yeah, it's beta 1 and up. And sex M it's for male. So it's when it's 1, when sex is 1. So that's beta 2. Okay, that's beta 2. Okay. So again, that's why we get values that are like negatives or higher than 1. There is nothing that put any constraints on the betas to be between 0 and 1. What we want is the survival to be between 0 and 1. The intercept and the slope doesn't have to be between 0 and 1, okay? And for detection, actually, what happens is that detection, because it's a probability, it's also on the logic scale that Mark is estimating its value, okay? So it's no surprise that it could be higher than 1 or negative. It's just that it's on the logic scale, so we need to back transform detection as well as the intercept and slope for the survival, right? So let's do it. We extract the results for the betas, and the betas for the survival are those ones. And there is also a beta for detection probability. It's just that there is no covariate. It's just logit of P is, let's say, beta 3, right? So we have beta 1, intercept for the survival relationship between, survival and sex, the slope of this relationship, and then the beta 3, the beta parameter for detection probability. And let's say we extract this parameter, the intercept, the beta 1. Okay, so we extract it. It's a matrix here. Beta, this object is a matrix, so we need to take the first row and first column. Okay, you get that. You extract that. You put it in this object logit phi for female. So it's this value 0.204, and now you back transform that using plogis. So plogis is the reciprocal logit function. You remember the logit -1 in R. It's a native R function, so you don't have to load any package or whatever. And you apply that on the 0.204, and you get 0.55, which is survival for female. It's female survival, right? Okay, now for males, you remember it's beta 1 plus beta 2 times the value for sex for males, which is 1. So it's beta 1 plus beta 2. So we need to extract the beta 1, which is what we did at the previous step, okay? And beta 2, which is the second row of this object beta here. So it's 204 plus 079, okay? So that's what I do here. I put everything in this object called logit phi m, and then we back transform this value to get male survival, and it's 0.57, right? So female survival 55 and male survival 57. Okay, so you don't want to do that. You don't want to do that by hand, I mean, but Mark and RMark are well designed, and you can get these results directly. You don't have to go through these painful steps. You can just extract the real parameters like we did before in the first live demo. So if you just take your object where you stored the results of fitting the model, you extract the element results, and from that you extract the real estimates, and you see these estimates. So you get survival for the group female. GF is for group female. Okay, don't pay attention to these symbols here. We'll have a look in a minute. 55, which is what we calculated by hand, and you get the survival for group male. Okay, which is 57, which is exactly what we got by hand. Okay, and detection probability is 0.90. What is this 0.90? It's the reciprocal, the back transformation of 2.227. You can try it at home if you want. I will maybe try it. Hang on, I'm going to open an R function. But I need to share. Now I need to share R. Okay. Now you see my R console. Okay. If you do P logis of 2.224, it should give you 0.9. Okay. Okay. So detection probability is also estimated on logit scale. I'll go back to the slides. Slides here. Okay. Perfect. Okay. And now that we have fitted this model with a sex effect on survival and constant detection probability, let's add it to our list of previous models, the ones with time varying detection or survival probabilities. So you collect models again, and then you see that this model with a sex effect is not that far for the model with a constant parameter, but still the model with a constant parameters, constant survival and constant detection probability is doing better in terms of AIC. Okay, so it fits better the data than the one with the sex effects. Okay. What about an additive effect like you would do in analysis of variance or more generally in a GLM? Additive effect of sex and time. So what we want is we want to have some we want to have time varying survival, but we want to have a different survival for males and females, maybe some kind of parallel variation over time between the two sexes. Okay, so it's an additive effect. So the interaction, it's an additive effect. So sex plus time. So you see that once you've defined those effects, then R mark is working the same way as the LM or GLM functions would work in standard R and in what you would do with a linear or generalized linear model framework. So you define this new effect, sex PT. Oh, okay, and sex plus time. I was about to do a joke about ChatGPT, but anyway, that's okay. So it's the end of the day. Sex plus time. Okay, and now you fit again. Thank you. I don't know who is laughing to my or kind of pretending to laugh to my joke, but thank you. Okay, sex plus time, and then you fit again this model. So you pass the arguments in this function mark, the process data as before, the design matrix, and now the parameters you're going to consider is this time, this additive effect of sex plus time that you defined at the here, and constant detection probability. Okay, you fit that one. Okay, you have a summary, you get more parameters. Okay, so the parameters, it's a bit tricky to compute the parameters, but let's try. Okay, so you have 7 time occasions, so it's 6 time intervals. Okay, and you don't estimate 6 survival probabilities for males and 6 survival probabilities for females. What you do is you compute 6 survival probabilities, let's say for females, and because it's an additive effect, you just add a difference with a single parameter for males. Okay, so it's 6 plus 1, these parameters that makes the difference between males and females for each time dependent survival probability estimate. So it's 6 plus 1 plus the detection probability, so it's 8 parameters. Okay, 8 parameters. And then you get these ugly estimates, negative values, values higher than 1. These are the betas. Okay, so you don't have a look to those. They are meaningless. You just extract the real parameters. And so what you get is, now you get survival parameters for females. You get 6 values for each time intervals. 1, 2, 3, 4, 5, 6. Okay, so it's 62% is the survival probability between 1981 and 1982. This one is between 1982 and 1983, and you see the idea. And then you get survival probabilities for males. The first one is for survival between 1981 and 1982, and so on. Okay, and detection probability is constant, 90%, which is high. I've seen that in the chat. It's very high, but it's okay. It's passerines and in the river, and Gilbert Mazola is a very good birder. Okay. Oh, nice graph. So that's survival as a function of year on the x-axis, and it's for in green we have males, and in blue we have females. So you see that it's kind of a okay. There is one subtlety. Yeah, the additive effect, it's on a logic scale. So you see that it's not perfectly parallel. Okay, the two curves, the two lines are not exactly parallel because the additive effect is specified on the logic scale. We say that the logit of survival is an additive function of time and sex on the logic scale. But then when you back transform the estimates you get on the logic scale, it's not exactly parallel, but still the survival estimates of females and males vary the same way. Okay, you have the same variation, and there is just this kind of this coefficient that controls the difference between males and females. But again, this coefficient is calculated on the logit scale, and when you back transform everything, you see that the difference between the two estimates are the two survival probabilities, males and females, are not exactly the same all the time. But it should be on the logit scale, it will be the same. Anyway, okay, this is everything I wanted to say, I think. This is the code to produce this figure. Okay, so you put, if you know about ggplot, it shouldn't be too difficult to understand. You put everything in data frame, so you need the x-axis, so it's here for both males and females, so it's between 81 and 86. And then you put the survival estimates, so this is the real values, and then you have the group effect, which is the sex here, okay, to control the color and the grouping in ggplot. And then you apply ggplot. X is here, survival estimate on the y-axis, and color is driven by sex. You add a line, and then I'm using this very nice color scheme. Okay. And then you may use collect models again, this nice function, to put everything together. And the model with an additive effect of sex and time is not doing better than the model with constant parameters, and you see it's here, right? Okay, continuous individual covariates, so wing length. Well, with no surprise, with it's in the data set. We have this wing length WG length covariate. So you just have to create a new list with a formula that uses this covariate, right? So it's the name of the column in the data set. So let me go back to maybe it was a bit, where is it? It's here. When we create the data frame deeper, we have this column, which we call sex, which is just an extraction of the sex column in the original CSV file. And then wing length, so WG length, is the scaled wing length that we extract from the original CSV file, right? Where is it? It's here. Okay. And then you call mark. Just amend the parameter on survival. You say that you want to have the effect of wing length. So that's what we've just defined here. Again, you fit this model, you get estimates on the logit scale. Oh, we have 3 parameters. What do we have 3 parameters? We have, you remember the relationship between survival and wing length. Wing length is a continuous covariate. So we have an intercept and a slope. So it's 2 parameters, the 2 betas, beta 1, beta 2, and then we have an estimate for a beta estimate, a beta parameter for the detection probability, let's say beta 3. Okay, so it's 3 parameters. If you extract the beta parameters, which are given on the logit scale, you get those values. And whoa, that was ugly. And then I want to have a nice graph where I would have survival on the y-axis and wing length on the x-axis to see how survival is varying with wing length. Here on the logit scale, when wing length is increasing, survival is decreasing because the slope is negative. Okay, on the logit scale. What does it give you on the natural scale between 0 and 1? We need to do a plot of that, to plot that. So it gets a bit technical because you have to define a grid for wing length and then estimate or predict survival for each value of that grid. Okay, so to do that, first you standardize wing length like we did in the creation of the deeper data set, but we do it by hand here. Then we build a grid of 100 values between mean wing length and max wing length. So we use this function in our sec for sequence. between mean wing length, scaled, because we fitted the model with a scaled wing length. So the grid has to be for scaled wing length, and max wing length, and we want 100 values for this grid, okay? And then we predict survival for each value, each of the 100 values of this grid. So to do that, we extract the intercept, and then we multiply the slope that we estimated with R mark times each value of the grid. So this gives you survival for each of the 100 values of grid length, of wing length on the log scale, and then we apply the back transformation to get survival for each value of wing length or each of the 100 values. You put everything in the data frame, and then you can do a graph. You may use, okay, so it's a bit like it's by hand here. There is this function in ARMA called covariate predictions that should be helpful in the sense that I think it does this step and this one for you. Those two steps are done for you using this covariate prediction function. Okay, and then ggplot. I put wing length on the x-axis and then survival that I just estimated, and I add a line, and I get survival on the y-axis and wing length scaled. You see, these values make no sense. It's just that this one is the mean value for wing length. Remember, wing length was varying between 40 millimeters and 100 millimeters. I can't remember, but some people, what did I do? Okay, so you see that as wing length is increasing, survival is decreasing, but it's decreasing from like 58.58 of survival down to let's say, why is it 56 and 56? There's something wrong here. It should be 50, 55. Why is it wrong? Anyway, so it should be 57, 56, 50. So you see, it's a 0.02 decrease in survival. It's not that big for the whole range of wing length. So there is an effect, but like the AIC was suggested, the AIC value of this model is really higher than the model with constant parameters. Doesn't seem to be a strong effect. What about a quadratic relationship? Whoa, I did, okay. So let's assume that there is an optimum value for wing length for which survival is the highest or the lowest. Okay, so it's not just a linear relationship, which is a bit awkward. But let's assume that there is an optimum value for wing length for which you get an optimal value for survival, meaning the lowest value, or so a concave or a convex relationship. Okay. So to fit this model, it's still a linear model. It's just that in the sense that the slope of this quadratic effect is going to be it's linear, but we just need to square the wing length value for each bird. So we scale the value, we scale wing length, and we raise it to the power 2, right? And then we process the data again because we have a new covariate here in deeper. So we need to process the data again, still with the group sex, okay? We build the design matrix again, and now we define a new covariate, which is the quadratic effect. So we have wing length plus the squared wing length, scaled. Both covariates are scaled before being squared. Scaled before being squared, yeah, that's it. And then you fit this model with the squared effect. And you get 4 parameters: the intercept, the term for the linear wing length, and the slope effect for the squared wing length, and the detection probability. So 4 parameters. You may extract the beta parameters, you may extract, and then you can have this nice plot where you have a quadratic relationship between survival. Oh, now it's working. Between 0.50 and 0.47. And so you see that as survival is increasing, you're reaching an optimal survival around the mean wing length, around here, okay? mean wing length being 0, because it's you subtract the mean of wing length to standardize this covariate. Okay, so 0 is actually the mean wing length, which is, I don't know, maybe 60 millimeter. Okay. Again, this is the code to produce this figure here, in case it's useful. And you can rank, you can include this model in your list of models and get AIC ranking. So you see that the quadratic effect is better, much better supported by the data, in the sense that this one gets an AIC value which is very close to the best model with constant parameters. Okay, so it seems that there is some signal in the effect of wing length on survival. Okay. Okay. So another sort of variation in survival is time variation. Okay. So for now, what we've dealt with is individual variation in survival probability or detection probability. It could be in detection probability as well. So it's characteristics that vary at the level of the individual. So the rows of the data set. Okay. Now, what if we'd like to have variation, environmental variation, so time variation, so covariate that vary from one year to the other. Okay. How to incorporate that in the model? So temporal covariates, say XT, could be, I don't know, temperature, for example, for each year. Well, same thing. We're going to say, okay, the survival between time t and time t plus 1 is beta 1 plus beta 2 times this covariate t, which capture the environmental condition between time t and time t plus 1. So this is where it gets very important to remember that survival is acting on a time interval between time t and time t plus 1, whereas detection probability is acting on a single time occasion. Okay, you capture at a single occasion. You survive over a time interval between two time occasions, between two sampling occasions, two capture occasions. You captured at a capture occasion, at a time occasion, okay, on a single time, right? So the covariates has to capture something either on the time interval or at the sampling occasion, okay, at a punctual, the single capture occasion. So you have to think about that before you're considering covariates, temporal covariates. So like I said before, there was something happening in this deeper system. There was an extreme climatic event, a flood, to be precise. Well, there was a flood on the second time interval and on the third time interval. So between 82 and 83 and 83 and 84. Okay, so actually around 83, something was happening, and we'd like to know whether it has an effect. It had an effect on survival. Okay, so how to do that? That's slide demo 3. Environmental covariate. That's what I said. A flood took place toward the end of the second survival interval and continued into the beginning of the third survival interval. Okay, so between 82 and 83 and 93 and 84 and 84. The question is, was survival lower in these two flood years? We're going to call them flood years. So to test that, we're going to have to go into the machinery of RMark and do some manipulation. So stick with me for a second. So we're going to have a look to the design matrix. So this matrix that kind of specify the effects, the general model with all the effects, time and group effect. So if you use this function head in R to display the first rows of an object, of a matrix or a data frame, and you say, okay, let's have a look to the design matrix for the phi parameter for the survival. And you see that there is this matrix, this table here, where you have this column age. We'll have a look in a minute to what it means, but this column time for 0, 1, so it should be time 0, initial time, time 1, and you have the sex effect. That's the group effect for individuals. Okay, maybe time. This one is there is a time with a big T and small t, okay? Small t and big T, it's just a different one, okay? So this is this matrix that we're going to modify. We're going to add to this design matrix a flood effect. So we're going to say this time effect here, which describes time variation. So first occasion, second occasion, third occasion, and so on. We're going to say, oh, there is something happening at time 2, well, between time 2 and time 3, and between time 3 and time 4, okay? So to do that, we're going to say, okay, you take this design matrix for phi, and you add a new column, which is just a column of zeros, okay? We create a new column by filling it in with zeros. And if you display the same object again, you have exactly the same thing, plus an extra column now, which is called flood, because we've called it that way, flood, and with zeros only, okay? And now what we want to do is to say, okay, this time interval between 2 and 3 and between 3 and 4, this one, we want to make it different from all the other years, okay? We want to specify flood years. So we're going to say this 0 and that one are different from this 0 and the other ones, okay? These two time intervals here are flood years, flood survival intervals, okay? So we're going to say, for example, like we did for sex, which one 0 and 1s, we're going to say, okay, the non-flood years are zeros and the flood years are 1s, okay? So it's a discrete covariate, but now it's temporal covariate. It's no longer individual covariate, it's temporal. So for some years, we're going to have a survival probabilities. And for flood years, we're going to have another survival probability that we're going to estimate. Okay, so that's exactly what I'm doing here. I say, okay, you take your function flood, your column flood, and one time is 2, or when time is 3, you replace the value of flood by 1. Okay? And you have a look to that. You can do it in a, well, you can do it step by step, and you can take, okay, when time is 2, you replace by 1, and then when time is 3, you replace by 1. And then you see that flood now, you have a 1 for the second time interval and a 1 for the third time interval. Okay, so these are your flood years, and the zeros are for the non-flood years, right? And now we have our new covariate. We just need to define this new effect, flood, in a list with a formula, okay, flood, which is actually this column here that takes value zeros when you are in non-flood years and ones when you are in flood years. You fit this model with a flood year effect. You get 3 parameters: survival for flood years, survival for non-flood years, and detection probability. And you get your real estimate for non-flood years. Okay, so that's for the group with the zeros, the first one, with zeros, T1. So it's 61. And for flood years, it's 47. So it's much lower in flood years. Okay, survival in flood years was much lower than survival in non-flood years. Okay, so these are our estimates, and detection probabilities is still constant in the way we fitted the model. Okay, we build the model. So we get very different estimates. Does it translate in terms of AIC values? Does this model do better than the model with constant parameters? We use collect models again, and you see that, wow, right away, the model with the flood effect and the constant detection probability is doing much better than the model with constant parameters, with an AIC of 666. Okay, it wasn't designed on purpose, this 666, but still. Okay, it's doing much better than the one with constant parameters. So clearly, flood has had an effect on survival, and it decreased survival. Okay. Last thing, what about covariates that vary? Okay, let's put everything together. So we had individual specific covariates, we had temporal covariates, so varying across rows, varying across columns. And now let's consider covariates that vary with both individual and time. So why do we need that? We need that for incorporating age, for example. Age is going to vary across time for an individual, and it's going to be different for each individual, okay? So in capture-recapture, there is something you need to keep in mind is that age is defined as the time elapsed since the first capture of the individual, okay? So in the case where individuals are marked, animals are marked at birth, it coincides with true age, okay? Because it's the time elapsed since first capture. And if you mark the individual at first capture, then it's true age, okay? But if you don't mark individual at birth, then it's just relative age, okay? It's age, it's time elapsed since the first capture and the first time you marked your individual, right? So you need to keep that in mind. You may think also to another example, body size across life, okay? Body size is evolving, is changing over time, and it's an individual and time specific, covariate, okay? The issue is that with this kind of covariate, age is not a problem, but body size, you record body size only when you capture individual, and you don't know about that. You don't know about this covariate when the individual is the animal is non-detected. Okay. So how to deal with this missing value issue? You may discretize. Actually, that's what we will see tomorrow. Like in small, medium, and large. So you discretize the covariate size, and you treat that as a state. So it's an individual time-varying covariate, but by discretizing it, you can use actually a transition between those small, medium, and large states to deal with the fact that you have some missing values, okay? So we'll see that tomorrow. Or the other option is to assume, I mean, you have to come up with a model to be able to fill in the missing values. So it's called imputation in the statistical literature. It's not possible. It's not doable in RMark, but in a Bayesian framework, yeah, you can do it. But yeah, that's another story. Okay, last live demo of the day: age effect. Age in capture-recapture models. So the cool thing is that there is something in the design matrix when you build your design matrix using the. So it's not the. You remember at that stage, that step. I'm going back to the very beginning. Yeah. Here, when you make the design matrix, actually there is an age effect that is built at that stage for you. Okay, so it's very convenient because. Hang on. Oop. Oh, sorry. Because you can use it in a straightforward manner. You just define a new effect with an age effect. Okay, so it's a phi.age, and you say, well, there is an age effect. So the thing is that you're going to have an age-specific full age on survival probability, full age effect on survival probability. So if you have, I don't know, 7 sampling occasions, you will have 6 age effects. Okay, let's do it. Huh? So it's a very data hungry model. But let's fit that model to the data. Okay, so we pass the usual parameters, the process data, the design matrix, and we say, okay, let's fit the model with an age effect, a full age effect on survival, and constant detection probability. What you get is 7 parameters. You get 6 age classes because you have 7 sampling occasions, so you can estimate the time elapsed since the first occasion, the first capture. Because you have 7 sampling occasions, you may have 6 age effect. Okay, plus the detection probability, so it's 7. And if you extract the real estimates, and if you assume that the deepers were marked at birth, which is untrue as far as I remember, but let's say they were marked at birth, so you get that survival between 0 and 1 is 55%, 0.55, and then survival between 1 and 2, between year 1 year 2 is 56, and so on. Okay, and you see that when you reach the last time interval for the individuals of age between 6 and 7, it's very small, but actually, well, it has some difficulties to estimate this parameter. Okay, this model is too data hungry, and it doesn't really make sense in terms of that's not what we're after. Okay, here what we'd like to do is to have two age classes, like young versus so 0, 1, and older than 1 individuals birds. Okay, so let's do that. So we're going to have to modify the design matrix. So that's what we did with the flood effect. We did it by hand. Here we're going to use this add design data function in our mark, which will just modify the design matrix slightly. Here we're going to say, okay, you take the process data, the current design matrix, and we're going to work on the survival and the column age. And we're going to say, okay, we're going to create two bins, one for between 0 and 1, so the young age class, and one between 1 and 7, so the older individuals, right? And we're going to call that age class. You could call that, I don't know, okay, between quotes. Here I use age class to make it, I could use 2 age class or whatever, but here it's age class, okay? So it will amend the current design matrix for you and create this new column in the design matrix, age class, which will take two values, a value for individuals that are between 0 and 1, what are aged between 0 and 1, and another one for between older than 1. Okay, and this covariate varies for each individual and each time interval, of course. Okay, and then you create a new covariate, H class, phi.h2, which is the effect of H class that we've just created, and you fit this new model. You get 3 parameters: survival for young and older than 1 year age individuals, and detection probability. So it's 3 parameters. You extract the real parameters. So for young survival, you get 0.55, and for adult survival, you get 0.59. Again, oh, I haven't done it, but you could also collect the models and compare this model. It doesn't really make any difference. And again, the deepers are not marked at birth, so it's really like relative age. It's time elapsed since first capture for individuals that were basically all adults, so it doesn't make any difference. Okay, it's not young versus adult; it's just first year after capture against after first year. Okay, well, it's 10 to 5. I think we're going to call it a day. I hope you enjoyed this first day of the workshop. Tomorrow we will regroup at 9 a.m. and I will start with multi-state models, and then Sarah will continue with matrix models, and we'll finish by 4, I think, in the afternoon. Okay, so same place tomorrow, 9 a.m. and we'll try to upload the videos, I think tonight or tomorrow morning, early tomorrow morning. Okay, so we'll see you tomorrow. Have a nice evening, and yeah, bye. Thank you very much.